Hey, all right, welcome here, students. It's hard to believe we're coming to the end, near the end, or maybe it's not so hard to believe. It's been a long journey. If you've been all the way with me since the beginning of Physics 110, we started with our unit conversions way back in Chapter 1, and we've been working along, and we're ready to start 31, and 31 and 32 is the same main topic and our last topic. So we're in this modern physics. We're in the most kind of recent discoveries of physics. I keep talking about the 30 years that shocked physics, although that was the last two lectures. This is even a little beyond that. This is then the whole discovery of nuclear radiation, nuclear energy, and nuclear medicine for a lot of you will be of the main interest. So this first chapter is on just the general properties of a nucleus and what kind of, well, what is a nuclear decay, and, you know, well, I'll just explain by doing the lecture. And then the next chapter, the last chapter, is on applications, and so hopefully you'll find that educational for you. And then, believe it or not, you should congratulate yourselves for going through a lot of chapters, 32 to be exact, in these last two semesters as we wrap it up to the end here. All right, so let me begin by putting here on the board that we are about to start here, chapter 31. And I want to cover the sections, well, maybe I'll put 31.1 through 31.6. Basically, that just means we're just not going to get time to do the last section. There's only 7 in there. So we're going to do most of the chapter, and there's a main long one here, so I think it's 6 or 5, where we actually get into some more mathematics. But the others of it is a little bit more conceptual. So as I was just saying, we're going to do here nuclear radiation. Or maybe I should say radioactivity. And your author starts off by saying, what do we mean by nuclear radioactivity? And so let me take a moment here to kind of summarize what kind of options we might get from our nucleus. And I think the best way is just to kind of show you picture number 1. And this is kind of the early steps, the first steps that scientists discovered nuclear radioactivity here. And he shows this picture here. And what this picture is down here in this lead box, if you will, there is some kind of sample. And then they say a radioactive source. And we know now there are many different types of source. In fact, I have a few that I will show you here in a second here. It's shielded with lead because one of the things we will talk about is lead does a really good job of stopping all of these options that I'm about to talk about here. But the early experiments went something like this. You just made a small opening in the lead box here, and these particles came shooting out, or you might even call them rays, or who knows. At the beginning, nobody knew what they were. But they did run it through a magnetic field. And so up here, you'll see a North Pole and a South Pole. So let's go back a few chapters. You remember doing that right-hand rule? Remember that Q, V cross B? Remember we said that if you had a moving charge in a magnetic field, there would be a force. And that was that Q, V cross B. Maybe I'll put it here on the board as a reminder of what we did. I'm not sure which chapter that was, 25 I want to say. But anyways, this Q V cross B says that if you have a moving charge particle, there is a force. And what's interesting here is if the force, or if the charge is positive, it's one direction, and if it's negative, it's the other direction. In addition to that, because the force is perpendicular to the motion, and so now we got to go way, way back. I guess this is back to chapter 6. This is physics 110 to our mechanics. That force would make it go in a circle. And the circle would depend, of course, on the amount of force, which is related to the charge and the speed and the radius. Anyways, by somehow detecting stuff moving through a magnetic field, you might be able to pinpoint, does it have a charge? Does it not have a charge? And if it does have a charge, then you can look at the radius of curvature to get some information about it. So the first experiments that were done were right here, and they come out and they have a little screen. It's a phosphorus screen, and so like we talked about last lecture, they could hit the phosphorus, make the electron jump up to another quantum level, and then as it decays, give off that light. That is fluorescence. And so that's what we were talking about in the last lecture. So they put this phosphorus screen to see if anything's coming out and see how much energy does it have, and they detect 3 different types. Now, there's more going on than that, and that's why I wanted to make a bigger chart than just what your author starts, but this is a great starting place. And so today, we often say that there are these 3 radioactive options, even though I will point out that I would say there's more than 3, but there is the alpha, the beta, and the gamma. And you can see they're just going down the Greek alphabet, alpha, beta, and gamma. And so what they end up getting here is that they discover that the alpha turns one way, so it's positively charged. The beta turns another way, so it's a negatively charged. And the gamma goes straight, so it must have no charge. And so they refer to these, and so I will just call that a alpha particle. Now, you will soon see as we go through the rest of this chapter that we'll later discover that these are actually 2 protons and 2 neutrons. And so that's yet to be discovered here. In the beta decay, it really can be subdivided into a beta minus and a beta plus. Now, the beta minus, as we will soon see, is actually then the electron. The beta plus is what we are going to call its antiparticle. It's almost identical to the electron, hence the name the positron, because it is the same mass, the same size, has all these wonderful properties, but is opposite in 2 ways. And one of those ways is it has the opposite charge. The other way is it is anti-material, and more on that later too. But these are our beta emissions. And this little diagram just shows the normal beta emission, the minus one, because again, the beta plus isn't going to make it that far in the experiment. Now, the third one here that they show, which we'll call the gamma particle, maybe we should refer it to as a gamma ray, because as we're going to see, this is like our electromagnetics. This is an electromagnetic ray. And so I will put here gamma ray, but it could also be X-rays. And so the high energy ones, usually when the nucleus does something, it's a gamma ray. If there's what we'll later call an electron capture, then they're a little lower energy, and so it's an X-ray. But either way, it's still just a high energy electromagnetic photon, like we were talking about in the last chapter, and like we talked about when we did our optics. Something that's not shown in this picture is the atom itself, or the nuclear itself, can split just into two smaller pieces. We call these two pieces the daughter pieces, and the starting piece the parent piece. There's also, again, not shown in that picture because it's really hard to detect, but neutrons can come out of this nucleus. And then finally, maybe the most complicated one of all is other neutral particles, very, very undetectable. Hence they're called neutrinos for little neutral one. And then those come in two flavors. There's what we call an electron type and its anti-electron type. That actually fits with the positron. So again, more on that. But I was a little disappointed that your author didn't begin the chapter with a bigger list. He just starts with the basics. And I don't know, maybe that is a good spot. And so that's where I'll start talking about the basics. The three fundamental ideas of an alpha particle, a beta particle, and a gamma particle. In fact, I like what he does next, where he then says, let's just kind of look at, kind of a historical point of view. And he says, what did these early scientists discover about these? And they found out that the properties of these are very different. Besides having a different charge and obviously a different curve, so they have a different mass, they just behave different. And so they found that these alpha particles can travel a few centimeters in the air. Now, luckily, they do travel a few centimeters. Otherwise, they would be under this list of they weren't discovered at the beginning. Because, by the time you take your sample and the magnet and your detector, you need a couple of centimeters there. And the alpha particle can actually go about that far. But remember, it's a particle, so it hits the air along the way, so it doesn't get very far. Now, the beta particle is actually smaller. Usually traveling faster, so it can go a little bit further. That's kind of the one I'll show you with, because it's the easiest one that I can show, because you can see it goes tens of centimeters. So it will go 10, 20, 30, 40 centimeters throughout the air. In fact, my beta sample's, right over there, but I'll keep it over there, so I'm a good 40 centimeters away from it. And so even though they're shooting out all these particles, they never get to me. Now, the gamma rays, they can go pretty far, and as it says here, and they don't even list air, because it pretty much doesn't even get stopped by the air. It would just go right through the whole atmosphere. But you can stop it with a couple centimeters of lead or a couple of meters of concrete. And I didn't bring out our little tank. It just dawned on me. But we keep all these radioactive samples in a container that's about this thick of lead, and so we kind of store it all back there. And maybe after we take our break, I'll bring it out so you can see it here. But anyways, just kind of want to give you a general idea of which ones travel the furthest here. So that being said, let me go on to this picture and the next. This picture is saying here that, I guess the same thing that I'm trying to say here, and I'll just jump to this last one here, but you can see it says, okay, here's the kind of the thing to remember. The alpha particles go a little bit and they run into things. They're kind of big, they're heavily charged, they're not moving that fast. These other things, the beta particles, penetrate a little deeper, and the gamma ones even more so. So maybe I shouldn't focus too much on that picture, because just saying the same thing that I just said in the table. But I did think that I should take a moment to look at one of the medical usefulnesses of this, and this will be talked about much more in the next chapter. But I know that for many of you, you're a little more interested in the life science of this. And so fortunately, there is good stuff about radioactivity. I know a lot of times we always think about the bad stuff. Remember I said these things are shooting out, and what's really dangerous about them is they shoot out and they're high energy. They'll slow down because they hit things, but if they hit human tissue, they can rip the DNA apart, and of course that can lead to all kinds of troubles and problems, and cancer being one of them, and different kinds of cancer. So in that sense, they're really dangerous and really, you might say, bad. But on the flip side of that, since they do destroy things, maybe they can be used, and they are used, this will be one of the applications we talk about in the next chapter, but they can use as a treatment for cancer, because you want to kill those cells. And so if you can direct these alpha particles or beta particles or gamma particles right to this tumor, maybe you could rip those cells apart and kill those. And so that's one of the medical applications that is in the toolbox of the medical doctor in order to cure somebody, or at least maybe cure is a little strong, but at least put them in remission, the cancer. Now, this one's a little different. This picture is showing what they call tracers, because what you can also do is put a small amount of this radioactive substance into some kind of compound, some kind of protein that gets absorbed in certain spots. Let's say you have cancer is another good example. If you had cancer, and bone cancer, that means the bone cancer, the bone is really, really active. And it needs a particular protein to grow, and so it's feeding that from your body. So if you add in a radioactive substance to that, then the faster metabolism, and that's where the cancer is, will start sucking up those proteins and concentrate the radioactivity in that tumor. And that actually could be part of the medical healing process, but it could be just as important as just giving doctors a chance to then put the person under one of these, what I said, this phosphorus screen, and just look at where is the radiation coming out of this patient's body, because that's where it got absorbed. And so that's what they're trying to do in this picture. They're trying to show here, okay, we've got, it looks like a lot of absorption here in the knee and here in the pelvic area. And so that's what they're kind of using. So I thought you would at least appreciate that in terms of the radioactivity, even before we kind of get to this idea of the radioactivity. For us, maybe I'll just take a moment to kind of show how can we detect these particles, how can we know if they are present. And so your author here talks about one option, actually talks about two. I'll show you this first one because this is a good one that I can show you. This is what we call a Geiger tube. And as the picture is showing, we've got a tube, and so in my case, well, this is my tube right here. And a very important part of this tube is down the center is a little thin wire hooked to a very high voltage. So on mine, I'll turn mine on. Here's the power supply with the power button. And here is what we call a high voltage cable. And so this little box here makes a very high voltage, and I can set it, and I'm going to set it to 600 volts. So I've got 600 volts coming over here to this little tube here, and so that center wire is highly, highly charged. Sound working okay? Yeah. No, I turned it off. Yeah. And so this is the charged wire. And then the application is pretty simple. Now we got to go back to the beginning of this semester where we dealt with electric fields, electric charges, but you might remember us doing this. You might remember, and I'll just kind of draw a little picture here. We said, what if you had a coaxial cable? And so you had this outside container, which maybe we will put, nope, I'm going to match theirs, negative. And the center wire, we make positive. And we said this would make an electric field. And the electric field would then go from positive to negative. And I'm only going to be able to draw this in 2 dimensions. But of course, I think you can imagine this being a cylinder case. And that's why I brought the real one out here so you can kind of see this cylinder case. But if there is any positives or negatives in this area, the negatives will be quickly drawn towards the positive, and the positives will be quickly drawn over to the negative. And so the Geiger tube is a very clever but very simple design. It just says if you have any of these fast-moving radioactive substances, this alpha, beta, or gamma particles, and it goes through this tube. And then one last piece to this design. This tube then is filled with a pretty complex organic molecule, sort of like your tissue that I was talking about earlier. And so if this particle goes through there, it'll actually take that organic molecule and tear it in two. And so you'll have a positive piece and a negative piece. And in fact, it'll go through and hit thousands of them and just tear thousands of them apart. And that's what your author is trying to show here. So coming through here, and I'll just call it a beta particle. I'm not sure which one they're saying this is, but I'm going to use beta particle in a second. So let's say this beta particle, which I'll call it an electron, comes ripping through this tube, and it tears 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, I don't know how many there, but it tears a bunch of molecules apart. Each of those, then, all the negatives move to the center wire and all the positives move out. And so what ends up happening is you get a pulse of electricity. And then with a little bit of equipment, and that's what this box is, you can then count how many pulses did you get. Every time a beta particle goes through there, or alpha particle or gamma particle, but every time some energy is transferred to this organic gas, it then beeps. And then fortunately this organic gas, and this is why they use that special gas, is then it will actually then float around and recombine and get ready for another one. And it doesn't take too long for this to happen, and so it's repeatable, repeatable, repeatable. And you can then just count how many particles, how many decays do you have, say, every second because of these particles. And that's this Geiger tube. So I'm going to turn mine on. Let's see. I'll turn on so it never stops. Here we go. And I'll even turn on my speaker here. And just with nothing real close to it, maybe I'll put my microphone there. And can you hear a beep? There's one. There's one. There's one. Okay. So Ron's shaking his head. So you guys can hear a little beep. And just nature alone in our area, we get 1 to 2 every second on average. In fact, why don't I do this? I'm going to change this counter to say, count for the next 10 seconds and tell me how many fly through there. All right. So I'll hit start. And I'll put my microphone close. So I've got 3. There's 4, 5, 6, 7, 8. Oh, no, the timer stopped. 7. Okay, so in 10 seconds, we got 7. So that's a little bit under 1 a second. But like I said, it's a kind of a statistical average. And usually when I do this, I get like 12 counts in 10 seconds in our general area. So sometimes I get under 12, sometimes I get more. This time I got quite a bit under, and so this is 7. But what I really wanted you to then see and to hear and to count is I'm going to take one of my radioactive sources. I'm going to put it on this tray, and so here's my beta source. And so if you could imagine right here, there's thousands of these little beta particles shooting out here. And I'm going to put it, and I'm going to get my microphone close enough so you can hear the difference between where it is now and when I actually slide it right under that tube, the entryway. In fact, that is so many. It almost sounds like it's on continuously. It almost sounds like beep, but it's just slow enough that I think you can hear kind of the separate on and off. So I'm going to count for 10 seconds. So let me reset and start. And I'm going to let it go for 10 seconds and just ask how many beta particles are now going into my Geiger tube every 10 seconds. And 10 seconds is up, and I got 788. And so that little beeper right there, beep, 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 beep. And I'll shut it off because that's annoying. Actually, maybe I'll just move the radioactive sample back to its container. But 788 then clicks is what would happen. And maybe you've seen that in the science fiction movies. You know, somebody's out there with the Geiger counter and it's all click, 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 and they finally find whatever it is they're looking for. And you just hear this. That's what the Geiger tube is. So this is the kind of the background of a Geiger tube. There's other detectors. Photomultiplier tubes do this best for the X-rays and the gamma rays. But they'll do it with any of the material. It's the same basic idea. If you remember the photoelectric effect we talked about in the last set of lectures, but in comes this radioactive particle, makes a little flash of light on the screen from the phosphorus. That then hits the first dynode and has a little photoelectric effect. And then what you do is that electron gets attracted here, and so you put a plus, they hit, and when that one electron comes in, maybe it hits so hard because you've made this such a plus charge that it comes in so fast, it hits 3 more off. And then you make this one even more plus, and so those 3 come racing over there with a lot of energy, and each of those 3 kick off another 3. So now we have 3 times 3. So maybe now we have 9 electrons. Again, you make another plus 1, the 9 comes in, and each of those 9 give off 3. So then there's 27, and I'll stop there. But you see the idea that it keeps getting multiplied, and eventually you get enough electrons that you can detect it. In fact, you might have said that about the Geiger tube, that why don't you just try to detect that one particle? But see, one little charge is so little, we just don't really have the electronics to do it. And so that little organic gas, as it raced through, kind of amplified how many charges I had so my equipment can detect it. And that's really what the photomultiplier is doing, the same kind of process. It's just trying to amplify it. Okay, well, if, like I said, that kind of helped, we'll go and start to look at the structure of our atoms here. But I did think that this isn't quite the same, but it's kind of nice to see. Maybe you've come across these plasma balls. These plasma balls there we go. Give it a chance to warm up. Kind of use the same idea, and what they do is they fill up this gas chamber with kind of a material that can easily break down. And then they put these electrons out here, and these electrons aren't beta emitters. They're just regular electrons from when we did our electronics here. But they will shoot through here, and they get attracted over here to my finger, and the fact that they get ripped apart and go back together is why they give off light. Can you see the light, or is it too, it's, yeah, probably hard to see. And maybe I'll shut down the lights a little bit, so maybe on camera you can see this a little better. All right, and so right now you've got this light going every which way. But watch what happens if I attract them more towards my finger here. And so I'll get them flowing through, and they just kind of break apart. And so again, not really a Geiger tube. Really, this is better for our electronics, but I thought it might be good to set it out here. And let me not do that. All right, but now I hope we can go to this next step and say, all right, let's put all this physics together. What really is going on? What are these little tiny particles that are coming out of the nucleus? And in fact, what are these other things that weren't originally discovered but were discovered in later years and so are talked about here as we get to the structure of the atom? And so maybe I'll leave those on the board here for just a moment and say, all right, let's look at what the nucleus looks like. And so we call this then the structure of the nucleus. Actually, more specifically, I will call it the substructure. And so what does the nucleus look like as we dive into the nucleus? And so let me put here on the board the substructure of the nucleus. And maybe even before I get to the substructure, let me go back and kind of draw a classical picture of an atom. And if you remember from last lecture, we drew a couple of these. Maybe I'll just start off by reminding you of the periodic table, which, reminds me, why don't I put that back on the screen here, because I want to talk a lot about the periodic table here. But if you remember last time, we said this first row represents the K shell, or principal quantum number 1 is what we said is more of a modern term. And then the second one, and we just go in alphabetical order, so K, L, M, N, or we just say the principal quantum number 1, we call it row 1, row 2, row 3. So let me just draw lithium over here. And so if you kind of remember our discussion, we said that as you look at the periodic table, there's a lot of very valuable information. Lithium has atomic number 3, and it's in the second row. It's the first one in the second row. So we said because it has atomic number of 3, it should have 3 protons and, well, a certain number of neutrons. Let me hold off on that. But these little black things are supposed to be these protons. And as I said, we're gonna talk more about these protons. We're going to talk more about these neutrons. These are the two that I mentioned were in the nucleus. And of course, in the last chapter, we focused then on these things on the outside, which we called the electrons. And this piece right here, if you again remember from the lecture, I said was the nucleus, and it's really small. It's in the neighborhood of 10 to the minus 15 meters. Whereas the whole atom itself is in the neighborhood of 10 to the minus 10th meters. You might remember me even mentioning that if you took our football field down here, our stadium here on the West Coast in Santa Barbara, and you think of the nucleus as the size of this football field, in other words, you expand the atom so the nucleus is as big as a football field, then the electrons are in New York City. They're over on the East Coast. And so that is 100,000 times bigger. So 100,000 football fields would get you to New York. And so that was kind of my idea to get you to see the atom. Because now today, I want to go into here. I want to go, what's going on inside here? What does this nucleus look like? And so we're going to see then that we're going to say then that a nucleus and an atom are made out of three things. The nucleus is made out of two things, protons and neutrons. And by the way, as a subnote, it's actually a bit more complicated. Your author doesn't go this far, but these are actually made out of things called quarks. And so we could go down that road, and I'm not sure why your author didn't. He did a lot of other pretty advanced things for you guys, but he didn't go that far. So I won't either. And so let's take it to this level, and maybe not as recent as the last few decades where we know what these are made of. So that's it, like I said, as far as your author goes. But this really is all we need to really get an understanding of radioactivity. So I think that's probably why that's as deep as your author dives into this. But let me just point out then, what I would call lithium, I'm going to refer to it as lithium-7. See, so the Li stands for the lithium. I put the 7 there because how many objects are actually in the nucleus? I don't know if you can see on the camera, but I deliberately tried to draw 3 of them darkened in, and those are the protons. And then 4 of them lightly colored because those are the neutrons. And we call it then lithium-7 because what this nucleus is made out of is 7 pieces of something, either protons or neutrons. It's actually a combination of the two. It's why we call them nucleons. And so collectively, these are referred to as nucleons. And so I have 7 nucleons. More specifically, though, I have 3 protons and 3 neutrons. Now, let's come back to this periodic table. We touched on this last time, but I really want to dwell a little bit more. Notice then that the lithium has atomic number 3. And that right there tells you how many protons it has. And so the atomic number always is indicating how many protons do you have. So if you have lithium-7, what that means is you have 7 nucleons, and 3 of them, because you said it's lithium, 3 of them have to be protons, so that means the other 4 have to be neutrons. And that's why we label it as lithium-7. Now, I got to admit, that alone is enough, but sometimes, just for additional clarity, we like to put the 3 protons in there. And I say clarity because that's really repetitive. See, once you tell me it's lithium, I know there's 3 protons. Which in the last chapter I said when it's neutral, it had 3 electrons. And so going back to our beginning of this semester, our positives and negatives, if we have 3 protons, which are positively charged, and we match that with 3 electrons, that's how nature wants to match it. So I was saying in the last one where we were focused on the electrons that I would have 3 electrons. And I should emphasize it wants to have that. Now, you could lose maybe an electron. And when we do that, we then refer to it as lithium ion. We said lithium now has a plus on it because it still has the 7 nucleons and the 3 protons, which would also mean it has 4 neutrons. So again, sometimes we like to put a little 4 right here for the number of neutrons. Now again, that's repetitive. And so I would say very few times have I seen the 4 out there. But quite a bit will I see the 3 protons with the lithium. That's pretty normal. But I'll say it again, you really only need the symbol for the lithium because that tells you how many protons, and then one number to indicate then how many total number is in the nucleus. Or I guess you could put how many neutrons and you wouldn't need that number because obviously those two together add up. Now, if we lost another electron, maybe we would call it lithium plus 2. But did you notice that every time I refer to it as an ion, and this is probably more of your chemistry background, it still hasn't changed the nucleus, right? The nucleus still has 3 protons. What makes it lithium is the fact that it's got 3 protons. And we could go through this chart and go anywhere. See, if I walk over here to this chart, I could pick on, say, in fact, maybe I will, because I think a good one for you life science people will be carbon. Carbon has 6 protons. But we have carbon 14 as well as the normal carbon 12. And of course, once I put carbon, there's really no need to put a 6 here, but I will. And just say that, hey, we have 6 protons. Well, we know that because it's carbon. But the normal carbon, what most of the carbon that makes up most of our human tissue and living tissue, whether it be a plant or an animal or a phylum, is that you have 6 protons and 6 neutrons. Most of the carbon has that. But some carbon. Now again, it's carbon, so it has 6 protons. But for reasons that maybe we'll get a chance to talk about, is energized by the cosmic rays, and so the carbon in the upper atmosphere actually ends up absorbing through kind of a series of process, but it gets an extra 2 neutrons. And as we'll see here, it doesn't like that. And this is the foundation of our radioactivity. If you have a scenario where you have a situation, and we'll see here, either too many protons or too many neutrons, they don't balance each other just right, the nucleus is unhappy. And we would say it's unstable. And so it shoots them out, and that's our radioactivity. And so we say it decays. It says it would rather change into something else, and it would rather eject it away. Kind of a sick example of that is, what if you ate some bad meat? Well, if you've ever had the unfortunate pleasure of eating bad meat, your body reacts right away. Your body says, this is not good. This is not a good place to be, and it ejects it right out of your stomach, back out your mouth, and all over the floor, and says, that's not part. And that's what I'm trying to say here, is this is what's going to happen to the nucleus. If we ever get a situation where it is unstable, however it got there, like we can talk about that, but it got there somehow and it ejects them out. And so we will see that we have a lot of atoms, and carbon-12 is one of them that is stable. It's happy. It likes this. This is a balance actually between an equal number of protons and neutrons. Now, let me be quick to say, that is not always the case. The stable place is not an equal number of protons and neutrons. Well, we'll talk about that in just a moment here. But for the many of them, or the lower number ones on the periodic table, that is true. And so if you get an imbalance, like in this case, we have an imbalance, it likes to change that. And it likes to then get rid of one of its neutrons. And in this case, as we'll see, it gets rid of a neutron and actually converts a neutron into a proton. And so what ends up happening is we get 7 protons, where's 7? Nitrogen. And then we're still at 14. Well, I think I'm kind of getting a little bit ahead of myself, because what I really just wanted to do here was to say we're going to use this notation, and we're going to use the periodic table a lot. We're going to use a notation to describe our elements on the periodic table here, where we're going to put a symbol. I'll just do capital X. So that capital X could be a symbol for lithium, could be a symbol for carbon. But what we're going to do is label an A and a Z. This A, as I just said, is what we call the nucleon number. The Z is what we call the atomic number. And the atomic number simply is the number of protons. How many protons are in that nucleus? And the nucleon number is actually then the number of protons plus the number of neutrons. That's what I was trying to say here in this little picture and this little discussion. Now, I also, this would be a good time in passing, especially since many of you have already gone through the chemistry, either here at the college level, or I think all of you have gone through a chemistry at a high school level. You will often hear a chemist refer to this as its atomic mass number. And so in case you're wondering about this number, let me emphasize, it's the same as the mass number. Now, my cheapy periodic table does not have the atomic mass or the nucleon number. But let me jump over here to our better periodic table and point out, and so I'll come over here to lithium, and as I look up there on the lithium, up in the upper right-hand corner, the red number 3, that's its atomic number. And then if you go down at the bottom and on the right-hand side, it says 6.941. And that's its atomic mass number or its nucleon number. Now, maybe it's worth saying a few things about that mass number here, because if you'll notice, for lithium, and maybe I'll put it here, I put lithium 7, but when I look up its atomic mass number, as you just saw, it was 6.9, what did I say, 41? 6.941. Okay. Now, I know what you might think. You might, well, that's not a 7. No, but do you see it's really close to a 7? And the whole reason it is not exactly a 7 is because what if I had this? What if I had something with 3 protons and 3 neutrons, so the total number of nucleons is 6? Well, it still would be called lithium, huh? I'll say it again. What makes lithium lithium is that it's got 3 protons. What makes aluminum aluminum is that it's got 13 protons. What makes carbon carbon is the fact that it has 6 protons. If you ever change the number of protons, you change the element from gold to silver to lead to whatever. And so note that the number of protons is the element itself. And as I mentioned earlier, if you change the number of electrons, it just becomes an ion. If you take 1 away, you call it a lithium plus. If you take 2 electrons away, you call it a lithium plus 2, but it's still lithium. In fact, you could even add an electron back. That's not easy to do for lithium, so maybe I'll pick chlorine. Chlorine loves to have, or is neutral at 17. Its atomic number is 17, and so it loves to have 17 electrons. However, it'll gladly take 1 more in to make a total of 18. And if it has 18, it's still chlorine. And the reason it's chlorine is because it still has 17 protons, but it has 18 electrons, and that makes it an ion. In that case, a negative ion. But I'll say it again, when you change the number of electrons, it now becomes an ion. If you change the number of protons, it changes the element. But what if you change the number of neutrons? What is it? Well, those we call isotopes, but it's still lithium. And that's what I'm getting at here is if I had something that had 3 protons and 3 neutrons, it's still lithium. In fact, if it had 3 electrons, it would be a neutral lithium. It's not an ion. But there is something different about what I'll call the normal lithium. The normal lithium has 7, and I can see that in this number. Notice that this number, 6.941, is a little bit lower than a 7, and here's why. If you just took a random sample of lithium ions, let's say you disassembled a lithium battery. So your phone breaks, you get a new phone, you go, hey, I'm kind of curious, and you take apart your phone and you have this lithium battery. They're usually about this long and thin. You go, hey, nice little lithium battery, and then you cut open the top and you go, oh, I have a lithium metal, and you take out the lithium and you go into the lab and you take away all the other junk that's in the battery, and all you have is lithium after all that. Probably not a good idea because that'd be a little dangerous. But if I have just solid lithium, what I would find is most of them have 4 neutrons and 3 protons. Some of them, a small percentage of them, have only 3 neutrons to go with their 3 protons. So what we put in the periodic table is an average. You essentially just weigh them and say, okay, what's the average of all of these? And again, since most of them have a 7, it's going to be close to 7, but some of them have a 6. And so you're going to report that as its atomic mass because on average, they have 6.941 nucleons in them. And so that's why in chemistry, we like to refer to it as its mass number because it's a strong indication of what is its mass. It's the average number of particles. Where here today, I'm really focused on its nucleon number. How many nucleons does it actually have? And notice, one particular atom of lithium never has 6.9 nucleons. It either has 6 or it either has 7. And that's the key thing here. All right, so this is just a good average. So when I look at that periodic table, I just kind of round everything to the highest number and say, okay, that's, not the highest number. I round it to the nearest number. And I could be up or down and say, what does it have? And so that's this idea. And I must admit, it's not perfect because your author does then say that if you look at the mass of a proton? So I will say, what is the mass of a proton? And what is the mass of a neutron? They are not quite exactly the same, nor are they really exactly one. More on this as we get to the end of the chapter, but let me take this as a moment to look those numbers up here in the book, because I don't know off the top of my head, but I put the book here at this location so I could see this thing right here, this mu. This is called its atomic mass. And so this is saying that a proton has 1.007276. So 1.007276 mu. I'm sorry, that's not a mu, that's a u. And for the neutron, it's looks like 8685. So 8685. It's still a double zero and still close to 1. But in terms of atomic mass units, you can see that a proton and a neutron are very close to the same. And that's why the mass of them will be the same as the number of them. Now, you might not have ever seen this very small unit for mass, but an atomic mass unit is 1.66 times 10 to the negative 27 kilograms. So you could imagine, since we're talking about little tiny objects, that these things are really, really small and really, really light. And that's what this section is all about, looking at the substructure. How many do we have? How are they laid out? Why are they laid out? How much do they weigh? And so with that said, you can hopefully now understand why what you learned as the atomic mass unit, or the atomic mass number in chemistry, is really the number of nucleons. And then it's kind of averaged, because that's what a chemist would do. They would take a sample, like I said, of lithium, and most of them would be 7, and some of them would be 3. So on average, there would be a 6.941 number of nucleons. Okay. And of course, they're not perfectly exactly 1 anyways. But this does help, because if you were to ask me how much on average does 1 atom of lithium weigh, I would say, okay, 6.941 atomic mass units. That is the mass of 1 atom of lithium. Now, by the way, in passing, but not real relevant for us here today, if you had 1 mole of lithium, then you would say that the mass of 1 mole is 6.941 grams. And I have a feeling most of you have come across that part of the periodic table. And that's the mathematical connection between the atomic mass unit and what I will call the standard unit for the metric system, the gram. And so that's why we put them in a big 1 mole setting. So again, this was just kind of my way of saying that you might have come across the atomic mass unit first, and you might have done it in grams, then that's because you were doing a whole mole. We're not going to do that. We're going to look at them individually. And so individually, on average, it's 6.941 atomic mass units. That is the mass of 1 atom of lithium on average. Now, if I actually know which one I have, a 7 or a 6, I could change that by adding these together, and then some other factors here. Okay. But again, maybe more of symbols than anything L2. Well, let me keep scrolling down here, because as again we talk about the structure, let me look at figure 13. Figure 13 does a little better job than I can draw. I'll try to draw maybe a three-dimensional clump, but since I can't draw it really well, I thought instead of doing a clump drawing, I'll do a real clump. Let me do this. Let me pick these green ones, blocks, to represent neutrons, and let me do the blue blocks to represent protons. And so if I was looking at lithium-7 here, I guess this is how I would structure it. I would say, all right, I got 3 protons and 3 neutrons. Now, as we continue with this discussion, you're going to see that because protons are positively charged, they don't really like to be next to each other, right? They repel each other. Remember, the like charges repel. And so maybe to make this a little more accurate, maybe I will kind of stack them in a way that they might prefer. So you can see then how lithium might prefer to have only 6 nucleons, 3 protons and 3 neutrons. But there is a kind of an extra one hanging around because it's more of a 3-dimensional stacking, better than I can do with this kind of 2-dimensional stacking. But they like to rearrange themselves so that they're comfortable. Remember that sick analogy I gave of somebody eating bad meat? If they're not happy, they're going to spit something out. And that's our radioactive decay, when the nucleus is not happy. And so again, that's why we need to talk about the structure of this atom. So this would be my model of lithium-7. Now, I won't try to draw or make things bigger than this, although maybe I'll make a small attempt here. But your author does a good 3-dimensional drawing, and he does the protons in blue. Oh, good, I matched. And the neutrons in green. Okay? And so he hooks those together and says, okay, why don't we start asking questions like, how big is it? Oh, when is it not happy? When is it happy? So in other words, when is it going to decay and when is it not going to decay? But I will say, as far as size-wise goes, and maybe it's best to see a giant clump of these. As I stack them in a big clump and try to make somewhat of a sphere out of it. And again, your author's picture is much better than mine. Can't you see that the radius of this sphere is really kind of determined on how many nucleons you have? In math terms, I would say this, that, okay, the size of this nucleus, R, is probably made out of something like A, which is this number here of how many nucleons do I have. And it's probably made out of something, I'll call it R naught, and this would be the radius of 1 nucleon. And it might be a little tough to see in 3 dimensions, so maybe I'll try a little stacking here. Why don't I start with, and I'll just do something that's kind of rectangular, and let me ignore the colors for just a moment. But I'll start with something that, again, is not spherical, but by extension of this, hopefully you'll see, because I have rectangular blocks, so it's kind of easier to do rectangular ones here. But I'm hoping you see that I would have something that I might say, if it was a sphere, you might say it has a diameter of 2. I've got 2 blocks. So it's 2 blocks by 2 blocks by 2 blocks. So it's 2 blocks high, it's 2 blocks deep, and it's 2 blocks wide. And I guess that makes its radius 1. Okay, so its diameter is 2, its radius is 1, and its volume would be 8 blocks. Do you see all 8 blocks? Right? There's 4 here on the top and 4 on the bottom. So I just want to make sure you got the math going here. So I've got a size of 2, but a volume of 8. Now doesn't that kind of make sense because it's 3-dimensional? So it would be 2 by 2 by 2, right? 2 times 2 times 2. That's 8. See, watch what happens if I make it 3 wide, 3 tall, and 3 deep. So I'll make it 3 wide, 3 tall, and it might be a little hard to see this back one, but I'll make it 3 deep. And for you, then I'll put it in front so that it's 3. And I'm trying to give you a visual effect of a 3-dimensional situation where I've gone from 2 to 3. But its volume is now 27 blocks. Did you see how many blocks I had to put in there? Isn't this 3 times 3 times 3? So in other words, the volume is a power of 3 compared to its size, its radius. The reason that's important then is because if we're going to pack a bunch of nucleons together, which we call A being the number of nucleons, its radius then would be the cube root of that, right? See, A is the volume. Its radius would be the cube root. So in this case, I would say A is 27. I have 27 nucleons here. And I get that with a radius of 3. And if I went to 4, well, I'd have to add a lot of blocks here to go 4 wide and 4 tall. But I eventually, and I won't bother to stack them all, but I'm eventually going to have 4 by 4 by 4. And that's 64 blocks. And so the size is 4, but the volume is 64. So I want to say it again. The pattern is to go from radius to volume, you cube it. Or to go from volume to radius, you take the cube root. That's why I'm going to then say that the radius of an atom is the radius of one little nucleon times A to the 1/3. That's because the volume of the nucleus is equal to the volume of one of them times A. And so we see here that the radius keeps getting bigger and bigger with the more nucleons that we have. But it really doesn't get that much bigger. That's what's kind of interesting. Did you see back here when I built this thing? I mean, I went and started with a simple atom, and I'll just go a 2 by 2 atom again. 2 by 2. And I suppose, now that I think about it, I maybe should have even started with a 1 by 1 by 1. But when I go from a 1 to a 2, I've only doubled the radius, but the volume's got 8 times bigger. And of course, when I got to 4 by 4 by 4, this is 64 blocks. And so I only went from a radius of 2 to a radius of 4. Or you might even call it diameter of 2 to diameter of 4. but the volume went up much more. In fact, a factor of 8, from 8 to 64, right? And so that's the pattern I'm trying to get you to see here. And so that's why, not a surprise then, that, and I'll put a box around this, that when we go to calculate the size of the nucleus, we will just say, take the radius of one nucleon, and again, proton or neutron, they're almost the same. Here I gave you their mass and said they're almost the same. Now let me give you their radius. The radius is, for all points and purposes, the same. And it's 1.2 times 10 to the minus 15 meters. This would be about a 1.2 femtometer. And so they're really, really small. So if I wanted to know the radius of, say, lithium, since I've been picking on lithium, I would come over here and say, okay, I've got a 7. That's how many nucleons have to fit in here. Some of them will have a 6, but most of them will have a 7. So with that in mind, I would come over here and take the number 7, raise it to a power of 1/3, and then multiply that by 1.2, 7 raised to power 3 times 1.2, and so we're looking, okay, let me try that again. 7 raised to a power of 1/3, and multiplied, there's my problem, I kept hitting the wrong button there, multiplied by 1.2, and so we're looking at about 2.3 times 10 to the minus 15 meters. Now, if I jump over to uranium, and so I'll pick uranium because uranium's the biggest one out there. Most of them are 238. There is 92 protons, and I guess the difference between that would make what, 146, so 146 neutrons. And by the way, I got all those numbers by looking at the periodic table. Actually, I had them memorized, but let me just double check. Yeah, 238 and 92. Okay, and so there's my uranium. But again, if I wanted to know the radius of uranium, the biggest atom, I'll go ahead and take how many nucleons do I have? So 238, and raise it a power of 1/3, and then multiply that by 1.2. And so we are looking at 7.4 times 10 to the minus 15 meters. So that's why at the beginning of this lecture I said all of our nuclei are roughly something times 10 to the minus 15. And so this is our biggest one, 7 times 10 to the 15. Whereas our smallest one, and this is lithium, but even smaller than lithium would go back to 1 nucleon, which is hydrogen, and so it would be 1.2. So the nuclei vary, but they all are times 10 to the minus 15. And that's what this whole section is about, what we, again, call the substructure. What are these things made out of? And so hopefully what you're getting out of all this is they're made out of protons and neutrons, and we can stack them together and, you know, look at their formation of them. Now, let's go back to our last lecture where we had quantum mechanics, and you might remember me talking about the reason why there is quantum mechanics. In fact, you might recall that I got real excited with de Broglie's work and his genius. Remember, we had most of that lecture, we were talking about the photon as being both a particle and a wave. We called it a wavicle. And it was de Broglie's genius who said, well, you know what, maybe the electron, which at that point in history scientists have only been looking at the electron as a particle. And so de Broglie's genius was like, look, if the photon has these dual behavior, perhaps the electron does. And then sure enough, that explains why we had the quantum effect, and that was the big ending of our whole quantum aspect. But let me take this one step further. I believe it was Gamow who then took this one step further and said, well, wait a minute, if electrons can be thought of as wavicles, can protons and neutrons be thought of as wavicles? And the answer is yes. And so if we think about our nucleus, which is made out of protons and neutrons, so we've got two objects, so it's much more complicated than just the electrons. But if we think about those two, we could do something like this. And so maybe I'll just make two charts. Here'll be my energy level. And maybe I'll put a little p here for proton. Well, I'll just put a p, and maybe I'll put then the lowest energy level. Let me call it E naught for the ground state, but let me also put here the neutron. Now, I'll be quick to point out that there is a lot going inside of that nucleus than we have time to digest and dive into. But I think this energy chart will help illustrate something really important here, and that is if you then had a single proton by itself, and that's it, the nucleus is kind of happy, saying, look, here's a single nucleus, here it is at the ground state, I have nothing else to interact. This would be, if I can change colors, kind of like we did in the last lecture, this would be like treating the proton as a wave bound inside a box that has this radius. And so if you remember our whole discussion of why there is quantum mechanics, we said the same reason as you have quantum mechanics is the same reason you have the harmonics in our acoustics. That is, if you have a string and it's tied on both ends, there is an integer number of half wavelengths that can exist between those 2 points. And that was a very exciting discovery for de Broglie and others of the reason why, Schrodinger I should say, and the reason why there is quantum mechanics. And so I just want to bring that back and say, let's apply all that quantum mechanics that we first did for the photon, then we later did for the electron, and now we are going to do for the proton and the neutron. Because I would say then, if you wanted to put another proton together with the first proton, it's not going to be happy. Why not? Well, number one, it has to have the next energy above it. And so it would look like this. The second proton, whoops, might have, let me try that again. The second proton has to have this extra bit of energy. Now, again, I should be real careful here because it's much, much more complicated than this. But I want you to see here that if this was the only thing possible, then I guess it would say, well, that's the only thing possible and I'm happy. But because there are these other things called neutrons, what can happen is it can decay or change, spit something out, and become then a neutron. And since there aren't any other neutrons, then this would go into the lowest state of the neutron. And so it would prefer to go over to here. And in fact, as we get to more and more complicated atoms, what you'll begin to see, and so I'll just do a bunch of energy levels. You have energy levels for the protons, and you have energy levels for the neutrons. And if that's all we had, you would say, well, they would be happy if you always had the same number of neutrons and protons. However, there is more going on than that simple answer. Remember, the protons, though, are each positively charged. And they don't like each other, so it takes energy to bring them together. Remember, like charges repel. So I say that because if I were to draw the energy levels for the neutron, they would be closer together. And so down here at the lower level, the atoms would be happy or stable if they had the same number. In other words, if you had too many protons, the proton would see an opening over here, and the proton would convert into a neutron. Or if you had too many neutrons, the neutrons over here would say, hey, there's a little opening over there, let's move over to that spot. Maybe kind of a silly analogy would, let's say this is a concert, and this concert is on a stage where there are 2 rows of seating. And if a bunch of people come in one door over here and start to fill up the seating way over here, they'll eventually look over to the other seating and say, you know, we can get closer to the stage. We prefer to be over there. And so they will actually leave this side of the auditorium, even though it was the closest one. This is where they came in. They came in as a proton, but they'll go, I don't want to be a proton anymore. I can get closer to the stage over there. And so they will leave this part of the stage and go over to that stage. And in doing that, they've got to decay. And that's where this lecture is going. They've got to spit something out. They've got to transform themselves from a proton into a neutron, or from a neutron into a proton. And that's one of the processes that I'm talking about here when they decay. But it's my way of saying then that using our idea of quantum mechanics from the last couple of chapters, I would think that the atom would be stable if it had an equal number of protons and neutrons. Up for a while, then, because the neutrons are closer together in energy, because again, remember, they don't repel each other, so all they have to do is change their wavelength. These protons got to change their wavelength, which is higher energy, and they have to overcome the repulsion between them. And so each of them is spread out slightly different. And as a result of that, at some point, you would start to get and prefer more neutrons than protons. So the early scientists actually measured this. And your author didn't try to explain this in terms of quantum mechanics, and I kind of hope that my explanation kind of helped. But what your author is really after is what we call the stability line. And so he makes a plot. And so the early scientists went ahead and started experimenting with just a bunch of different protons and neutrons combinations. You know, maybe they did something like this, and they put 5 protons together with 1 neutron. And they instantly discovered it decayed, it spit apart, it broke apart, it did all kinds of things. It was not happy. And so by experimenting with different number of protons and neutrons, you can then discover which ones are happy and which ones are unhappy, which ones change, which ones decay. And that's where this chart came into play here. And so along the x-axis is the number of protons, and along the y-axis is the number of neutrons, and there's a dotted line, dot, 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 that is a slope of 45 degrees. This is a line where the number of neutrons equal the number of protons. And as you can see, down here at the beginning, the number of neutrons equaling the number of protons is pretty stable. In fact, if I jump back over here to this periodic table, you'll see that really well here in the numbers. Maybe I'll pick on carbon right here. Carbon has 6 protons, and if you look at its atomic mass or its nucleon number, it's 12, so that means it also has 6 neutrons. So it's balanced, 6 and 6. Nitrogen, same thing, 7, and there would be 7 neutrons because it's 7 and times 2 for a total number is 14. Look at oxygen. Oxygen is an 8 and, again, atomic number of 16, so that would be 16 minus 8, yeah, 8 neutrons. So 8 protons and 8 neutrons. Now, fluorine, if you double it, you should be about 18, but it looks like it's closer to 19. So in that case, we have most of them with 1 more neutron than proton. But since it's lower than 19, that means some of them also have 18, so there's an equal number. And of course, if you just have 1 more, decaying away to something else, there's not really a spot available. Again, my silly example would be like when you're in that auditorium at the sound stage. If you're in the 11th row back, and you look over to the people sitting on the other side, and they go back to the 10th row, it doesn't do you any good to cross over. Because when you cross over, you still got to get in the 11th row. And so that's what happens if you just have 1 more proton, or 1, in this case, neutron, 1 more neutron than proton. So being off by 1, I would still call it in that same range that they're trying to have equal numbers. They just have an odd number and they can't move over. In fact, I should have said that with lithium. That's what happened with lithium, because lithium had 3 protons and 4 neutrons. At least the majority of them have 4. Some of them have 3 and 3, but some of them have 3 and 4. But again, that 4th neutron doesn't do any good to change into a proton. It just now becomes the 4th proton and there's not available. So again, like that auditorium, if you're the 4th row back and you look over and the protons go to 3 rows back, if you cross over, you still got to go to the 4th row. There's nothing to be gained. There's no preference one way or the other. So again, I would call all these lower ones equal number. In fact, if we get back here to neon, you'll see it's 10 and 10. However, as you get to some of these higher numbers, and let me just go all the way down to the big boy, there's the uranium again, the biggest one that I just mentioned. Remember when we got to uranium, by that time there's 92 protons, and I guess I got to subtract that again, 146 neutrons. And so we've got a way more number of neutrons. But I'll say it over here on this energy diagram, we are at the same energy for them. And so you can fit in 146 neutrons, and it would be at the same spacing as 92 protons. Otherwise, they would shift over here. And so that's why we have this chart. And you can see that the chart, again, starts off equal number of neutrons and protons, but then it kind of angles up, always keeping to the high side of a larger number of neutrons than protons. And because it's all about trying to get to the lowest energy, or by my silly analogy, trying to get closest to the stage to see that concert. And that's, again, like we did with the electrons last chapter, where the electrons wanted to jump down, that quantum jump down, and give off a photon. So they wanted to get rid of something. They wanted to get rid of a photon. They still stayed electrons, but they got rid of something. They ejected a little bit of energy, and that's the main point we're getting to in this chapter, is that's what nuclear radioactivity is, this ejection of something out of the nucleus. And whatever comes out of the nucleus is designed to make the nucleus more stable. And so if a proton has to go to a neutron, well, then a positron comes kicking out, that beta plus. But if a neutron wants to go into a proton, then a beta negative particle comes out, or the alpha particle or the gamma particle. And I haven't gotten that far quite yet, but I think you're seeing this whole idea of the reason it's stable and its stability. In fact, this will give me a chance then to really get to the grand finale of this chapter, that and the math, where I say, let's look at this chart here. this chart here kind of explains in, I'll call it symbols, that I was trying to show you. Let me start with the beta minus decay. I think that's the easiest one to talk about. I think it's the third one down on this chart. So alpha, beta, no, second one, beta. Okay, right here. Since it is a beta, here's the symbol we're going to use. So we're going to say it is a beta particle, and we are going to give this numbering to it, a 0 and a 1. Now, I guess I've erased it over here, but you remember our general symbol is like this, an element where the number of nucleons go here, and the atomic number, that's the number of protons, go here. Okay? So why do we give it this symbol? Well, we give it this symbol because really what a beta particle is, or a negative beta particle is it's really an electron. Meaning it is not a nucleon. It is not a proton. It is not a neutron. So I would put a 0 right here because, I'll say it again, it is not a proton. It is not a neutron. And so it deserves a 0. I'm going to put a negative 1 down here because the charge is positive for a proton, but it is negative for an electron. And I'm going to go back to the beginning of this semester and say, you remember that principle of conservation of charge? It still applies. And so if I want to keep track of what's going on in this nucleus, if I have started a process with, say, lithium, so 3 protons, and then all of a sudden one of the protons disappears and becomes a neutron, that one positive charge has to show up somewhere. And this is the way we can keep a balance for it, by saying that the beta negative, and that's why we call it beta negative, because it has the effect of having an atomic number or a charge of -1. Watch, this will probably make more sense when you see this in terms of a reaction. So let me start with the general idea that I have an element that has an atomic number of Z and a nucleon number of A. So it starts here. And as I was trying to say in this little energy chart here, let's just say that it has too many neutrons. So let me put a neutron here, and a neutron here. You see this fourth level here, this neutron is looking over here and saying, you know what? We can lower our energy. Of course, because of conservation of energy, we've got to eject that energy. But we can lower our energy, or in terms of my weird analogy of getting close to the stage at a concert, the people who came in from this door over here on the right and sat here look over and they go, we can get closer, and so they move over to the other row. And so if we move over here, we are then going to make a neutron now become a proton. But watch this. Then this new element, which I'm going to call it X prime, to say, okay, I've become something new. And it is then going to have a charge or an atomic number of Z plus 1. It's going to increase by 1. Now, see, that's what happens when a neutron becomes a proton. But of course, because of conservation of charge, it has to eject something to to A, lower its energy, and B, take care of that charge. And so these are our conservational principles: conservation of energy and conservation of charge. We got to make sure that we have the same number. We also have this thing that I will call conservation of nucleons. Baryon number is probably a better, fancier name here. But what will happen then is those have to add up also. So notice, by doing this, this object comes shooting out with energy, and so the energy over here matches the energy over here. Remember I said we would lower from this energy level down to this energy level? So the atom itself has less energy, and what happens is this thing goes shooting out with a large amount of kinetic energy. That was this earlier experiment here with this Geiger counter. That's where that energy came from. There was a change from a neutron to a proton, and lower energy in the nucleus, and so something had to come out. This is really no different than what we saw with the electrons in the last chapter, where we said the electron was at an excited state, and as it tumbled down to a lower energy state, or as it quantum jumped to a lower energy state, it emitted a photon. And that's exactly what I'm trying to say here. There's something emitted. Now this isn't a photon, this is a whole nother particle. Really it's an electron, but it comes shooting out. And what I want to show you then is I have three conservational principles that I have to follow for this to happen. The driving force behind why it wants to happen is the atoms trying to get at a lower energy. But in the process of getting to lower energy, we have to conserve conservation of energy, conservation of charge, and conservation of baryon number, or conservation of nucleons. And so what I'm saying here then is the energy is conserved because something comes shooting out at a high rate of speed. The charge is conserved because if you add up all of these here, so z plus 1 minus 1 is equal to z, yep, it equals to z. And then if you add up all the baryons here, A plus 0 is A, they match. And so one of our decays, what I'll call the easiest decay, is the beta decay, the beta minus decay. And there it is. And so your author, I think, does a good picture of this right here, because he says, see the parent right here? See that little, I guess it's a neutron. He kind of gives it an oddball color out. It's going to convert into a proton. And in the process of converting into a proton, it's going to have lower energy, so we got to account for that energy. We've got to kick it out. We also got to account for the charge. And now, since a neutron just became a proton, there really is no worrying about the number of baryons, the number of nucleons. So we're good with that. And so that is one of our decays. Now, maybe another one to talk about is the one right below it. This is a lot like the beta decay. It's a positron emission. I call it the beta positive decay. But it's the same kind of thing, that I'm going to put here beta with a plus and a 0 with a plus. Maybe a better symbol. You know, I guess he has the beta. He doesn't really put the plus or minus, and I like that. But here's the positron decay. And so, like I said, the positron decay is nature's way of, again, ejecting this. But in this case, we're going to eject from the nucleus not a negative object, but a positive object. So in other words, we have too many protons. And so the proton's going to convert back into a neutron. And so if I change my drawing here, let's say I don't have a neutron here, but I have 4 protons and only 3 neutrons. This atom's going to say, I'm not happy, or maybe I could say I would be happier. Again, the analogy at the concert. If this is the best seating you got, you'll be happy. I'm just happy I got to the concert. Yay! And if this side's all filled up, then I'm not going to try to move. This is the best I can get, and I'm happy with it. But if there's an opening over here, okay, and so if we don't have enough neutrons, this proton is going to say, I want to move over, and I want to change from being a proton into a neutron. And in the process of doing that, it's lower energy. That's why the atom wants to do that. The atom wants to go to the lowest energy. But in the process of doing that, we have to balance our conservational principles. Conservation of energy, conservation of charge, and conservation of baryon number, or nucleon number. And so what I will then have is a new atom, which we'll call the daughter atom. So this is parent, this is daughter. And in this case, to account for the energy, a little tiny particle called a positron, one that's probably not as common to you, that's why I didn't want to start with this one, but I want you to think of it just like the electron, but with a positive charge. And that, of course, carries with it a +1, which is why if I put a Z-1 here for the daughter particle, I can see that my charge is conserved. That is Z-1, and then added to a +1 is still equal to what I started with, Z. So the charge is conserved. And you can see that it has now Z-1. This daughter one is one less proton. And that's exactly what I'm trying to say here. This proton over here converted into a neutron. You have one less proton. And so if this was, let's see, 1, 2, 3, 4. So if this was, let's go to the periodic table here, what is 4 protons? So this would be beryllium. Now it would be an unstable beryllium. Let me get a little closer. I can't quite see the number over here. What's the stable beryllium? But it looks like the stable one has 5 neutrons. And probably would even be happy with 4 neutrons. But in my picture, I only gave it 2 neutrons. And that's why it wants to then jump over and make another neutron. So in other words, this number here would be 4, so beryllium, and now we go down to 3. So we go down to lithium. But keep in mind then, what also happened is the number of neutrons increased by 1. And so we went from 3 to 4. And so we've got our stable lithium again. We've got 3 protons and 4 neutrons. And again, that's how we're going to write this. Now across the top, I guess I would still put an A here and a 0 here. Because again, the daughter still has the same number of nucleons. All we did was change a proton into a neutron, but it's still the same number of nucleons, or baryons is a fancy name. So that number doesn't change. But notice then that the positron doesn't have a number up there, it's 0. So it would be A plus 0 still matches the A. And so those are our beta emissions. And again, those might be the easiest ones to talk about. Now, let's go and say, well, what is an alpha decay? And so this first one listed is what we called alpha. You probably should learn that an alpha particle is a total of 4 nucleons and 2 protons. That's the same as a helium nucleus. So if I come over here and I look at my periodic table, right here, here's helium, helium-2. And, helium has 2 protons, and we call it helium-4 because the helium then has this 4 right there, which means it has 2 protons and 2 neutrons. And so the early scientists didn't know what they had. They just called them alpha particles. But the alpha particle is then what today we would call a helium nucleus. Now it turns out, and like I said, the chart for the energy levels is much more complicated than I've given it credit for. But I'll just put a little box around this first couple of steps. because 2 neutrons connected together with 2 protons is actually a very, very stable scenario. These 4 objects like that a lot. They really like to be hooked together. Here's why I say that. Because if you had an atom that had a lot of protons and a lot of neutrons, even if their energy levels were balanced, so in other words, neutrons would not want to go over to protons and protons would not want to go over to neutrons. There's no reason to do that. There is a reason for the top 2 of each to break off and leave. Because remember, these protons all repel each other. And so if you start putting a bunch of them together, and I'll pick on uranium again, because uranium's the big boy in the chart here. And so uranium, look at uranium. I mean, uranium's got these 92 protons. And so if you imagine my energy chart going up and up and up, and I'm way up here at 92, the last 2 are getting pushed away from the other 90. At some point, they just say, yeah, I would prefer to go somewhere else because you're just pushing me away so much. So for big-sized atoms that have a balance of energy, and I don't want to say balance of protons and neutrons. Remember I said earlier that when you start getting a bunch of protons and neutrons, you get more neutrons than protons, okay? And so in this case, I'm all the way up to 146 neutrons and 92 protons. And they're near the same energy. They don't want to convert a proton to a neutron or a neutron to a proton. But the last 2 protons are being pushed away by the other 90. And eventually, at that size, it breaks off. And so uranium is radioactive in the sense that it does an alpha decay. And what happens is it would look something like this. So you'd start with the parent. And maybe for ours, I'll put uranium. And so I've got 238 for the number of nucleons and 92 for the number of protons. And it says, you know what, that's just too big. Again, we don't have room for neutrons to move over to protons or protons to move over to neutrons, but it's just too big. So why don't 2 of you protons, and since you like to group up with 2 neutrons, why don't you 4 group together and go off on your own? Again, maybe a silly analogy is kind of like growing up. And eventually there's just too many adults in the house, and it's time for what were the kids that now are young adults to move on, move out of the house, start your own family, have your next generation, move on. Or maybe the colonial days. There's just too many people in Europe and you got to put a bunch of people and say, go to America and start over there, but just get kicked out, whether kicked out from England or kicked out from Italy, whatever the case is. But it's just kind of a sick analogy, but there's just too many. Time to move on. It's better to move on. So this is what I'm trying to say. There would be another way for it to decay. We'll call this then the daughter atom. And then notice then, because of conservation of energy, we have to have something being kicked out with a lot of energy. And also because of conservation of charge, they have to add up. And so this daughter is going to have an atomic number that is 2 less. Because remember, we're just kicking out a grouping of 2 protons and 2 neutrons. And so that's why we put a 2 here. And notice then that Z minus 2 added to 2 add up to Z. Okay? And then in the top row, notice then that this would be an A minus 4. Because we are kicking out 2 protons, and 2 neutrons, a total of 4 nucleons. So that's why we have a 4 up here. And so again, when you add A minus 4 plus a 4, you get your A. So in the case of uranium, uranium kicks out 2 protons, and so it actually changes from, remember, it's the number of protons that determine what it is. And so if I look on the periodic table here, uranium goes down to thorium. And so now it has 90 protons. And so this would be 90 protons. And of course, we would be at 234 nucleons. And of course, plus the alpha particle that came shooting out, which is 2 protons and 2 neutrons. And so this would be the decay process, and that's listed here as an alpha decay. And so there it is. And so here's the parent, here's the daughter, and here's your author trying to draw an alpha particle. It's got 2 protons and 2 neutrons that go shooting out. So again, all 3 principles are conserved: energy, charge, and nucleon number. Okay? And so those are the 3, I'll call it the 3 easiest ones to talk about here. By the way, in passing, since this is such an important one here, this uranium-238 has changed into thorium-234. But that's not a stable one. So this is going to keep on decaying. Let's see, let me come over here and see what the stable one is. Yeah, so thorium-232 would be stable. And so 34, we're got too many neutrons at this point. So a neutron's going to change into a proton, and so it's going to go under a beta decay. Anyways, and this process continues. And so as a side note, we'll talk about this in the next chapter, this is a nice decay process because it starts with uranium and it keeps changing and keeps changing and eventually ends up as lead. And there it finally gets to a stable one after protons and neutrons keep getting changed and kicked out. And so it goes through a series of alpha decays and beta decays. And we'll go through that chain reaction here in a moment, or I'll show you a chart of it. Maybe I won't take the time to go through all of it. We got some math to do, and then we need to go into our break and then do some examples. But if I continue on here, let me jump down. I'll skip the electron capture for a moment because your author did the gamma emission. And the best way I can describe a gamma emission is really the same way we were just doing this last chapter, where we talked about an electron being in an excited state and jumping down to a lower energy excited state. In other words, the electron is still an electron. The electron didn't change into anything fancy. Nothing came kicking out other than the energy associated with a photon, and that's what the gamma decay is. So the gamma decay, and they give the Greek symbol here for the gamma, but they put a 0, 0. And so I'm going to put here gamma 0, 0, because again, if I start with the parent, and so here's an A and here's a Z, and let me come back to my kind of weird energy chart here. Let's just say, and I'll just go to our lithium. So I've got these 3 protons, and I've got these 4 neutrons, and I would say at this point the atom is happy, it's stable, and we call that lithium-7, and lithium-7 will just stay as lithium-7. There's no reason for a neutron to change to a proton, or a proton to change for a neutron, or no point in 2 protons grouping together and go shooting out. They don't have a bunch of other protons kind of pushing them away. Okay, so everything's stable here. However, what if somehow, and let me not get into the somehow, but what if somehow this proton here, or this neutron, doesn't really matter, but the one here gets excited up to a higher energy up here. But it's still a proton. It just got up to a higher energy. So something had to happen to make that occur. And if you remember last chapter, what I did is I hooked up the light bulbs and I ran electricity through them. And I got the gases excited by running electricity through them so that then we could see them de-excite and give off the photon. Basically the same thing's happening here. Is I have a proton and all I'm going to do is say the proton is going to lower its energy. It's still going to be a proton. There's no changing of a proton to a neutron. There's no kicking out of anything with mass, but there is a lower of energy, and that's what the photon, right? The photon was this electromagnetic particle duality thing that just had associated with it energy, but it did not have associated with it a charge. It did not have any kind of indication of it being a proton or a neutron, so it doesn't have a baryon number. So that's why we're going to label it this way. We're going to say a gamma particle is really a photon. It is a high energy photon, but it has 0 charge and 0 nucleon number. And so really this reaction is kind of boring because the daughter is the same thing as the parent. It still has the same number of nucleons. It still has the same number of protons. The only thing that has changed between the parent and the daughter is that it has ejected some energy from it. So we will often put and say, well, the parent is in a high energy state, and so it lowers its energy to become the daughter. That's the only thing that changed. In fact, I'm going to look at your author's notation. What did he use for the gamma decay? Oh, good, he did use the little star. So he puts a little star here, and he says X with a star then becomes the daughter. Oh, and I should have put a prime to indicate that it's the daughter like I did at the other ones, but at the same thing, the daughter is no different than the parent. It's just lower energy. And so this one, like I said, is also a fairly easy one to understand. And he does a good job in his picture because he just says, here's the parent, here's the daughter, and the only thing he's done is given it a bunch of energy. And so saying that what's going to come out of here is an electromagnetic wave. And so that higher energy is really high. In fact, that kind of happens here with our electron capture. And so if you have a parent, and I guess I would say in all these other reactions, I have talked just about the nucleus. Never did I worry about the electrons that were around the nucleus. But in this case, this only makes sense if the electrons that are orbiting around actually fly into and get captured by the nucleus. Doesn't happen often. It's not an easy process. In fact, some of the processes of quantum mechanics, these can only happen if you remember me talking a little bit about your chemistry and those s orbitals and the p orbitals and the d orbitals and the f orbitals. This can only happen with an s orbital. Can't even happen with the d orbitals or the p orbitals for reasons we better not go down that road today. But I will say then, if we then make an electron, and I'm glad it's still here on the board because this beta minus is really an electron. And so notice for the electron it has a -1 charge and no baryon number, no nucleon number. So this would be a 0 and this would be a -1. Now a good example of this might be, what if I had something like well, let me put my energy level here together. Maybe I will do something like this. Maybe I'll make it so that I have a situation where I have a bunch of protons and a bunch of neutrons. It looks like right now I got about a 4 and a 4. But this right here could come over and become a neutron. And if this energy level is a little lower, there's something to be gained, but not much. And so making a proton become a neutron is often thought of as a beta plus decay. And it would do it on its own if there was such a large energy difference. But if there's only a small energy difference, it might just be sitting here going, there's not much to be gained. Again, my silly analogy at the concert, if you're way back here in row 100, and you look over here and see an opening in row 99, you're like, okay, there's a little to be gained, but I'm not real motivated to get over there. I mean, it's only one row. I'm already 100 rows back. Is there really much difference between 100 and 99? And the answer is, well, no. So I need some kind of encouragement, if you will. And so maybe there's some attractive person over there. And I'll go, okay, now I'm motivated. I mean, granted, it's better to see the concert, and that's what I'm here for, but maybe to sit by these attractive people, maybe who knows what will happen by the end of the concert here. So I'm motivated. And that's kind of what I'm saying here, is that this thing is thinking about beta positive or a positron decay, but it's not real motivated because there's not much of a difference. But if one of its own electrons hits it, it might grab it and say, okay, now I'm motivated here. We can group together. I'm a proton and you are an electron, and you come together, I can group together and we can make a neutron. And so what ends up happening is the daughter then becomes one less proton, because we have changed a proton into a neutron. And of course, the number of nucleons doesn't change. Okay? But that capturing may actually give it a bunch of energy. And so maybe I should have put another row up here. So it captures it. It becomes a neutron, but it's a neutron up in a higher energy state here. And then it decays away. Or maybe even there isn't as high as that. There's what we would call a metastable state. And so it quickly becomes a neutron, can't stay there, so it got to drop down. And that then would release then a photon. And since it's usually not as much energy, it's an X-ray. I'm going to come over here and see what your author gives for the symbol. Oh, he just spells out X-ray. Okay. So I will put here X-ray. And so the electron captures often give off an X-ray. In fact, this isn't too much different, but a little different than what we talked about in the last lecture, where we said we could make our X-rays by shooting electrons at a tungsten filament. And what happened is we would hit the inner electrons on the K-shell and pop them out. And so then they would tumble back in. And so they tumble back in, of course, not all the way into the nucleus, but they give off these X-rays that we calculated. This is kind of that same thing. The electron is already inside, and maybe it's in the K-shell, and now it's going to go from the K-shell into the nucleus. And so instead of us having to get it excited and then let it come back to the K-shell, it's already in the K-shell, and we're going to bring it into the nucleus. And it's about that same energy level. So it would be in the X-rays. Which one am I missing here? I think we did them all except the spontaneous decay. And yeah. And the spontaneous decay was the one that I said at the beginning, where it could be just that the atom split. Again, if this helps, I'll come back to this energy level diagram. Imagine a bunch of protons and neutrons. And remember I said in the alpha decay, the last two want to break off and leave. the last two together with 2 neutrons, and so a total of 4, that alpha particle is pretty happy and it breaks off. I would say this last one is really kind of the same thing. Except sometimes when they break apart, instead of just 2 protons leaving, a whole group of them leave. And so instead of just a minimum leaves the environment, the whole thing splits in half. And so the whole thing, you know, again, kind of a silly analogy here, but instead of the analogy of the alpha particle where the kids grow up and there's just too many adults and so a few of them leave, let's say this is a big family that lives in a big house and they just don't get along anymore. And they're just going to split, and half of the family is going to go this way and half of the family is going to go that way. Or maybe a better example is the bees, because my neighbor raises bees and has all these beehives, and at least 2 or 3 times a year the population of his beehives gets so big that a big group of those bees decide to leave and make their own colony. And so inevitably, somewhere in my backyard is this giant swarm of bees starting to form a beehive here. They've left and split. There's just not enough room and resources for them in my neighbor's backyard, and so they seem to love this tree in my backyard, and so they break off and they start making a beehive over there. And fortunately, my neighbor's really good about it. He says, hey, if that ever happens, come over and tell me, and I'll make sure. So all of our neighbors around him, we call him like 3 or 4 times a year, and he comes over and he's got his stuff, and he piles it in here, and as he piles it in, he takes those bees, and there's a wilderness area up in the hills he likes to take them to. So he goes, well, they're ready to leave and make their own hive, so I'm gonna take them up to the hills. Anyways, this last one is just like that here, and so it would look something like this. You would start with your parent, which would have a certain number of protons and a certain number of nucleons, and it would split off. And so let's see how your author labels it. You'd get 2 siblings from this. So he calls it an X prime and another X prime. Okay. So X prime and another X prime. And he says, he does an interesting label on this. I don't know if this is good or bad. Well, yeah, I guess I'll follow his lead. I'm not real crazy about this, the way he does it. No, I'll tell you what, I'll give you both. You can use his, but I would do this. I would say maybe this over here only has B left of the nucleons. That means this would be over here A minus B. So if you added these 2 together, you get A. And that's what I'm trying to show you. This is how we do our conservational principles of this, that the number of nucleons have to add up. And so this top row here has to add up. So if we start with A, and then it splits. So let's just say this is 70. And then if this is a 40, this has to be a 30. And the same thing with the charge. If this is Z and it breaks apart, and you only have, I'll use Y here, then this would be Z minus a Y. It can do even better than that. And it usually does. Because do you remember that little chart of stability where it was not stable when exactly the number of protons equaled the number of electrons? I mean, the number of protons equaled the number of neutrons? And so if you're stable and you cut that in half, since it's not along a line, when you cut them in half, they're probably not stable. Or you don't even have to cut them in half, but if you cut them into 2 pieces, let's say you cut it into 40% and 60%, those probably aren't stable. And they're probably not stable because they have too many neutrons. So it is quite possible for the big atom that not only does it split, but as it splits into 2, there's a bunch of free neutrons that go flying out because nobody wants them. They're unstable. And so let's just say neutrons, and of course neutrons have no charge, but they have one nucleon number. And so let's just say that I have C of them. That means this here, the C times this needs to be somewhere in here. And I'll just put it, I should have gave myself more room. So this would be A, the original, minus the number of nucleons from this one, minus the number of nucleons here. And so that's a very common process. And in fact, that's what your author shows you right here. Your author shows you, and again, now that I look at the map, maybe he did it better than me. He said if you start with a bunch of nucleons, which add up to A, B, and C, they will then break apart from the parent, and there'll be three pieces. There'll be two daughters and a bunch of neutrons, which he would say C neutrons, and his picture shows three. And of course also a lot of energy, I should emphasize. So those neutrons will come shooting out at a high rate of speed. So we conserve energy, we conserve the number of charge and the number of, or the amount of charge and the number of nucleons. And so there is our conservation. And of course the Z plus Y would of course be Z protons for the first daughter and Y protons for the second daughter. And so again, just a bunch of high energy neutrons. And so that's the spontaneous decay. And so those are all of our options of our nuclear decay. And of course your book emphasizes the alpha, beta, and gamma, but there are a few others that I thought needed to be explained in more detail. Now, there is more to this chapter, but I've been talking for a while, and it's probably a good time to take our 15-minute break. But when we come back from the break, let's put some numbers and some calculations, because I've been talking more about how and why they decay. I have not done any numbers with how quickly they decay, and how many of these particles do we have. And so we need to do some math. And so when we come back from the break, let's talk about the math of it, and then let's do some example calculations, and we'll call it then done for the chapter. All right, so see you in 15. Okay, hey everybody, welcome back here. We hopefully you had a good break, a little relaxed. Of course, you guys on video, you can take a break anytime, and so hopefully you do take breaks often. It's a lot of information. But let's finish up this chapter. It's time to get into some math and talk about some of the rates of decay, the different kinds, and we'll even learn a few things along the way here. And so let me give you an equation. Let me give you a new number here, or some new ideas. But let me use the word capital R. Capital R, I'm going to then call this the decay rate. Maybe a better name for this is its activity. And so its decay rate is simply this. R is dN dt. Now, N is just like when we did the ideal gas law way back in physics 110. This is just the number. How many atoms do you have, or how many decays do you have? So how many alpha particles do you have, or how many beta particles do you have per second? And it hopefully seems somewhat reasonable to say that the decay of the atoms, that is the activity of them, would be proportional to, well, how many do you have? In other words, if I have a box of 100 atoms versus a box of 200 atoms, the fact that I have 200 more means it would decay twice as much. There would be twice as many decays, because what we're going to say is every atom is equivalent. So again, a box of 100, that's a small number, so maybe I should do 100 billion. So a box of 100 billion atoms is going to have a certain number of decays, and a box of 200 billion would have twice as much, because you could think of that 200 billion as being two boxes, each of 100 billion, and each of them having the same rate of decay as the 100 billion. And so we like to put this in words and say it's directly proportional to n. Now, if we put those words into equation, it looks like this. dn dt equals, see, is equal. And when you say something is proportional, you say it's multiplied by it. And then there is some proportionality constant. And your author uses the symbol lambda. We'll call this the decay constant in a second. I'll put a negative in there because this is the rate at which the atoms decay, the rate at which they go away. So it's a negative sign. In other words, the change in the number of atoms I have is negative. So if I start off with 100 billion, a little bit later I'm going to go down to 90 billion. In other words, it's a decay. It's a negative number. The change in the number is negative. So taking these two numbers as positive, then with a negative in front would indicate that this is a decay. Now, here's the neat part about this math, is we could solve this for the number of atoms. This is what we call a differential equation, a little bit of calculus, not a real hard one, fortunately. And so we could actually solve this. So let me solve it. This is one that we would say is separational by it can be separated by the two variables. So let me put everything with an n on one side and everything with a t on the other. So I'm going to take the dt and move it over to the right, and I'm going to take the n and move it to the left. And so there is our differential equation that is separable. So the reason for that is so we can solve it. And so we've done this quite a few times in the semester. Here's some good news. This is the last time. We're done solving any calculus, well, except for the homeworks and the test and that kind of stuff. But the next chapter really is about not anything new. It's about applications, and we're done with our 2 semesters. All right, so let me go ahead and then integrate both sides. And so maybe you would say something like this. I start with a box of atoms that decay. So in other words, at time equals to 0, I start with n naught, a certain number of atoms. And then a little bit later, 1 second, 2 second, 3 second, whatever time you want to put, so I'll just put t. A little bit later, we are down to n. And I suppose we could call it n final. But I'll just leave it as n. And so if we solve this differential equation, or now we integrate it, I'll get a minus a lambda. And on this side, I would get t evaluated from 0 to t. And this is that fancy one, but since we've seen it a lot, and you guys have been telling me the answer really good, this is the natural log. So this would be the natural log of n evaluated from some initial to some final value. And if we put in our limits, then we have ln of n minus ln of n naught. And on this side, we would have lambda t minus 0. Again, another nice property of logarithms is when you take a difference, you can write that as a quotient. And then finally, getting rid of the natural log by raising both sides to a power of e, I would have n over n naught, e to the minus alpha t. And then finally, I get what I'm after here, which is a mathematical equation that would say, how many atoms do I have after a particular time? They're decaying away. And so what I wanted you to see then is the mathematics that fortunately, and the reason we call these natural logarithms and natural exponents, is this is what happens naturally in nature. In other words, if you start with just a simple idea that the change is proportional to how many you have, this could be like population growth. If you wanted to study how many rabbits you're going to get, the change in the number of rabbits is proportional to how many rabbits you have. So if you have 1,000 rabbits, they grow by a certain number. But if you have 2,000 rabbits, that's like having two sets of 1,000. They grow by that same amount. Now, of course, there's other issues like, is there enough resources for 2,000 rabbits? Then 2,000 rabbits don't have the ability to grow as fast as the 1,000 rabbits. But if those two groupings of 1,000 have the same resources as food and predators as the box of 1,000, then the rate is proportional. So population growth follows this exponential. And anything that decays away, in other words, it decays away in proportional to the number that you have, it's going to follow these. And so a lot of things in nature, and so that's why we call these the natural exponents, follow these exponential decays. And so it would look something like this. And so again, if you were to start with 100 billion, you're going to, after a while, get less and 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 less. And if you were to ask yourself, how many do you have after a period of time, they would follow this mathematical equation. And so that's why I said a good name for this alpha then is the decay constant. That it is a rate of which it is decaying away. Now, it might be a good point to talk then about the units. And you can see it in this equation, but you might see it a little better in this equation. You're talking about a number per time. How many decays per second? Decays per second. And we can list that in two ways. If it's a small number of decays, we refer to it as in units of a brachio. I don't think I spelled that right. And I don't use this much, and we won't either. Brachira. Or BQ. More common is a Curie, after Madame Curie. And we'll have a problem with her and some of her great work that she did and her radiation, and she ended up getting the Nobel Prize for her discovery of all this great radiation stuff. And so as you'll see, the number of decays, if it is, looks like that's 37 billion. So 37 billion decays in 1 second is a Curie. And so I prefer that unit. But either way, we'll go ahead and note that that would be the unit to measure this decay constant. How many decays per second? Okay. And so that, like I said, is the unit for this decay constant. I guess it's also the unit, you can see it for the rate, because this doesn't have a unit. And so how many decays per second? Same unit as our decay constant. Now another little fun side fact in this is actually taking the derivative of this. Now let me not actually take the derivative, because we have that, of course, right here. This is that decay constant. But if you think of it in terms of rate, watch this equation. And so dn dt, which I'll call the rate, okay, so that's this step right here, is equal to minus alpha times, and I'll come back here, the number. How many do you currently have? And if we put this equation in there for the current number that we have, n naught e to the minus alpha t, and then write it in terms of a decay rate, you will see, oh, sorry, bumped my sound again. I think it's working here. You will see that this rate here and this number, and so I will put, actually maybe with the minus sign, so I will group those together. That would be the initial decay rate. Right? That's what this part of the equation would say, right? This would be saying put n naught here. This is your initial decay rate. And so then you would have this same exponential factor. And let me put a box around that, because that can be very convenient too. So in other words, not just how many atoms do I have, but if I hook up my Geiger tube and I look at the initial rate of decay, whatever number I get, it's going to get lower and lower and lower by that same mathematics, that same exponential decay. And so this is a nice little feature where we could talk then about the changing rate of decay, in other words, the activity. And so a lot of times this is really what we're interested in. A lot of times we're interested in not really how many atoms do we have or have left, but how many beta particles or alpha particles or gamma particles do we come shooting out. And so we can start with a certain rate when we first build our sample, and then realize that later on it's going to go down. And so again, kind of a nice mathematical property. Now I'll say another nice mathematical property, and let me leave those two equations alone. But it's sometimes really nice to ask, how much time would it take before the number of atoms is cut in half? Or maybe, and just as nice, ask, how much time would it take before the number of radioactive particles, like the beta particles, is cut in half? And that might be a more popular word. That's called the half-life. So let's run through some math here. Why don't I start with saying, all right, I have a certain number that I start with. They're going to diminish according to this decay equation. And I will then have this many. And if I ask that question, how much time will it take before I have half of them? What you're really saying is n is equal to 1/2 of n naught. How much before I have half of them? And then fortunately, I get a pretty simple equation since the n naughts cancel off. And so let me put in a new symbol here. I'll call this t 1/2. So in other words, if I put in what I'm going to call the half-life, how much time does it take before I have half? And I'll point out, I can say half the number of atoms, but I can also say half the amount of activity. Okay. And of course, to solve this, we got to get it out of the exponent. So that's where the natural log comes into play. And so on this side of the equation, I would get minus lambda t to the 1/2. And on this side of the equation, I would get the natural log of 1/2, which I'm going to write as the natural log of 2 to the negative 1 power. And then, of course, what's nice about that is what we call the log rule, where you can move the exponent off the top and in front of the natural log. And so I get a negative 1 times the natural log of 2. And that's helpful because there is a negative now on each side. So I'll cancel those off. And I finally will get what I was hoping for, which is the time, what we call the half-life, would be the natural log of 2 over lambda. And so the decay constant and the half-life are really one and the same. Once somebody tells you one, you also know the other. And I think that we need both, because I think from a human perspective, we like to ask the question, how long before half of them are gone? But from a math question, we need the decay constant to go up into that exponent. And so I'm going to hopefully keep this here on the board and remind myself, okay, there is a mathematical connection between this lambda and the half-life. Because as you will see in the problems, you will be asked to solve these, and they'll talk about the half-life. They'll say, oh, the half-life of radium is, or the half-life of carbon-14 is, or the half-life of cobalt-60 is. And then they'll say, okay, now that you have the half-life, tell me what the number of atoms is left over. Or tell me how much activity do I have. And of course, to do that, you need the lambda. You need the decay constant. And so that's what I wanted to emphasize. So there's this math, and I'll come back to that. And then there's one other piece of math, and maybe I'll show you your data table here, and we'll do a calculation from maybe it first. Let me turn off the periodic table. Oh, here's a fun chart. This is the one I was mentioning, the decay of uranium, and the first one was an alpha, and then looks like it's 2 beta. We were looking at it, and the next one was, the first one had to be an alpha, and the second one had to be a beta. We went that far. But there is a very famous chart that I want to tie in with chapter 28 here mathematically. And this, somewhere in here, further down, I guess. I think I'm getting close. We're still here. And this is it. Because we want to play on this chart in the next chapter when we get into applications. And it's saying here that if you take what we call the binding energy. All right, so remember before the break, I had that energy diagram where I said as you go up the chart, there's more energy from the protons, and you go up the chart, there's more energy for the neutrons. And so these things are hooking together. They are binding together. So as they bind together, they're releasing energy. They want to give off that energy. In other words, they want to be hooked together. This would be a good time to mention something that I didn't say. I did say, remember those protons that they're both positive charge? Remember how they both want to push each other apart? And it's harder to put a couple of protons together than it is for a couple of neutrons together. That's why the stability chart that we talked about started off with equal number of protons and neutrons, but eventually got more neutrons than protons. I said that spacing was there because you didn't have the electrical charge, but I just implied that they want to come together, that they want to hook together. There is this thing called the strong nuclear force. Maybe the best way I can describe that is to say, if you think of these as, well, I'll just go to the colored blocks over here. If you think of these colored blocks as maybe having a little Velcro between them. And so what they want to do is when they get close enough, hook. And so they do bind together. And so a proton and a neutron, all of our nucleons, remember that fancy word baryons, they want to hook together. and another proton will come along and it will also want to hook. Now remember, it wants to get pushed away from the other blue one here, the other proton. So it's probably not going to hook this way, but it doesn't mind doing that. And so if it has a little neutron between them, it's kind of happy. And of course, like I said, that's why you kind of get an equal number of them. And of course, my model is a straight line, so it's not a fair picture. But they like to stack together here. And so there is a certain reduction of energy, a certain binding force holding them together. And that's called the strong force, the strong nuclear force. And so in case you were wondering, why do they hold together anyways if there's a bunch of protons? That's why. And the protons then don't hold together quite as well as the neutrons, because again, the neutrons are being pushed apart here. But what this chart is a measurement of how much energy do you get for each bond. And they call this then the bonding energy, because at first it increases, peaks up to a maximum, and then tapers off. And so if I plot on the horizontal axis the number of nucleons, and so here it is, atomic mass, 50, 100, 150, 200, so here's A. And here is what they call the binding energy. How much energy do you get for each nucleon? You can hopefully begin to see why it has this special shape. And in the next chapter, we'll talk about how useful this special shape is. In fact, I'll hint towards it here in a second. But you will notice that at first it goes up. Now, it is kind of complicated. It does have a bunch of squigglies in it, so it's not this nice straight line. But I'll just give the general idea is when they hook, each hook has a certain amount of energy. I guess a good example would be in your chemistry class. You could have iron and oxygen. They want to hook together. Yes, the iron is all hooked with other iron, and yes, the oxygen is all hooked with other oxygen, but they would prefer then to separate off and make iron oxide. You'd call it rust. I guess hydrogen and oxygen is the same thing. You can then take hydrogen and mix it with oxygen, and it would like to bond together, of course release a lot of energy, and that's this whole idea. There is an energy released once they hook together. So when you have a small number of nucleons, they want to keep bonding together more and more and more and more of them. You can kind of see this if I just had maybe a simple two. I had one proton and one neutron, and they stick together. If you could come along and connect another proton or another neutron, maybe we'll put the neutron there. Especially this last neutron. I mean, watch it. It actually hooks up twice. And so maybe this one you'll say only once. And of course, you're just looking kind of at a two-dimensional. But if you have like a little opening here and you put another one in there, there would be like this bonding all around it, all these connections, all these Velcro connections. In other words, it likes to do that. It likes to make lots of hooks, lots of connections. And so the amount of energy per each bond gets more and more and more and more. And so at some point, but before I get to here, at some point you can begin to see that one of these protons or one of these neutrons, we have so many that it's tucking inside, that when you tuck it inside, maybe there's like 6 or 8 connections from the other protons and neutrons around there. I mean, it's really grabbed tight. It's not like at the beginning where you just had 2 and they only grab each other. That's it. When you put one that has a bunch in there, it hooks up maybe 6 to 8 times. And the point here is then you get more and more energy per each nucleon as you make it bigger and bigger and bigger. And so in that sense, because of that strong nuclear force, nature wants to have a big nucleus. However, as I said earlier, those protons have a positive charge. And as you start piling more and more in there, they start pushing each other more and more and more. And so eventually you get to a point, and you begin to see it right here, where you reach, I'll call it the maximum effect of the strong force, because now as you make your atom bigger and bigger and bigger and bigger, the energy per each bond goes down. And so it's still bonding, it's still strong. In fact, this little magical point right here happens at iron. And so iron over here on this periodic table has an atomic number of 56. And so we like to say, from a science point of view, 56 is the most stable. This is the one where you start shoving in more of them. They're happy. Now you're getting to the point where you have too many protons. And again, iron has 26, I believe, 26 protons. And at that point, now you start shoving more in there. It's happy. I'm not saying it's unhappy. But the energy per each bond is going down. And so this little chart goes down. And so be careful. When it goes down, I'm not saying it's unstable. I'm not saying it's radioactive. Now, at some point, it does get unstable radioactive, and that's when we said we got to uranium. That's when we got to the big boy. That's when we finally said there was just too many protons. And so once we got to 92 protons, it finally said, my 2 protons and my 2 neutrons, we're going to group up and we're going to go. And so I'll stop the stability right here at, uranium 230, well, I'll say 238, but even 238 is kind of past the stability of it, just barely past the stability. In fact, uranium has an extremely long half-life, billions and billions of years. That's why we still have uranium around from the beginning of our solar system, is because it takes so long. So is it unstable? Yes, but barely unstable. And so it takes billions of years for these things to decay. Their half-life is somewhere in the billions of years. Anyways, here's what I'm trying to say. And here's what I'm trying to lead into both the math and next chapter, is that if you have smaller atoms and you bring them together, there's a release of energy. It's like taking hydrogen and oxygen and burning them. Bringing them together, there's a release of energy. In other words, they want to get more towards the iron. And that's called nuclear fusion. Don't confuse that with nuclear fission, because we also do that, and we have better control over fission than fusion. But if you have big atoms and you take them apart, they're actually more stable or better energy when you take them apart. And so nature has given us 2 ways to kind of use the energy stored in the nucleus. And one way is we can take small atoms and group them together, but another way is we could take big atoms and break them apart. They both work. In fact, I came across a curious question. Once in a while when I need a break, I like to read Quora, and they email me like crazy because I read a few articles, and so it's a social media that you can just kind of get lost in. But they're always good questions, and of course they kind of know what I'm feeding on. But one person asked a question that was kind of an insightful question that I thought was obvious because I knew the science, but it was a good question. They said, how in the world could you get energy when you split an atom, but also get energy when you merge an atom? And I thought that was pretty clever. Anyways, and so that one grabbed my attention, and so I read it. And so I like to read the questions, but really I like to read the answers. I like to see how people are answering it, and I think it helps build my skill as a teacher and say, okay, how can I answer something like this? What was going on in that person's mind to even ask that question? But again, I just want to say we're going to talk about releasing of energy, and this side of the graph will be nuclear fusion, and this side of the graph will be nuclear fission. Well, with that being said then, let me keep this graph here. Let me keep some equations around, but let me wrap up the chapter by saying, let me do 5 examples for you. And my first example will actually be one right from the book, because it is going to follow this discussion. And so I thought this would be a good place to get us started. It's example number 7, but it's going to allow me to tie in this discussion with next chapter, and together with our special relativity of chapter 28. And your author just says this. He says, could you calculate the binding energy per nucleon for an alpha particle? Yeah, here it is. So example number 7. Calculate the binding energy per nucleon for helium-4, the alpha particle. And so I'm going to come over here and say, all right, the binding energy, and so I will call it BA, binding energy, would be the total energy divided by 4, right? Because there's 4 particles. So remember, the binding energy is per nucleon. And coming over here, somewhere in here, this will give me a chance to use an equation that I mentioned at the end of our special relativity one. Remember that E equals mc squared. And so this is the one that, as I said, at the end of our special relativity, I got all excited, and hopefully you did too, where Einstein realizes for the first time that there is a connection between energy and mass. Before that, we said there was this principle called conservation of energy, and that you couldn't make any energy. Well, this is saying you can make it, or maybe better, it's saying that mass is a form of energy. And so if you can reduce the mass, you would gain energy. And so I guess the other way works too. You could take a bunch of energy and convert it into mass. And so what your author says here is, what would be the total energy, including and really only focusing on the mass energy of 2 protons and 2 neutrons? Because if I then hook them together, what would then be the mass of a helium nucleus? And so I'm going to do this. I'm going to say that the amount of energy, mc squared, with these 4 separate objects is different than the amount of energy of these 4 objects. So I'll use the numbers from your book instead of kind of look them up here, but your author simply starts off by saying, if you go to Appendix A, you can look up the mass of helium-4, and it's 4.002602. So 2602,004. That would be in atomic mass units times c squared. And we can debate if we want to change that to kilograms so we can get the energy in joules or not here. But I am going to just say this is what I have so far. Now over here, I guess I need to give myself quite a bit of room, because it's going to be 2 times the mass of a proton plus 2 times, I wonder if I can fit it in here, the mass of a neutron. And so again, I'll just use your author here. And he says, okay, if you come back and you look at a proton, it is this 1.007825. So 7825,001. So I'll kind of squeeze it in there. So there's the mass of a proton. And the neutron was a little more than that, if you remember. Here it is. It was this 8665. So 8665, 001. And grabbing my calculator here for our first example, you'll see that there is more energy stored in the mass before I put them together. So then when I put them together, there's less energy or less mass. And because of the principle of conservation of energy and the principle that mass is an energy, this is that release of energy. This would tell us the bonding energy. And then if I divide by 4, I get the amount of bonding per each particle. All right, so let's see what I get here. 2 times 1.007825. Let me add that to 2 times 1.008665. And I get 4.03298 mu c squared. And again, this is the point of this example here, is see how if you were to weigh the 4 objects independently before you put them together, you get a mass, an energy, that is greater than when all 4 of them are put together. Meaning, according to the principle of conservation of energy, as we take these 4 objects and fuse them together, remember I said at the beginning of that chart, you'll gain or release energy as you go from smaller to bigger. I'd say I've gone from 4 1 objects to 1 object of 4, and I fuse them together. And I want to leave those equations up there, so let me work around them. But I would then say that the release of energy, so let's see if I can fit it right here. Energy final minus energy initial. And so I'm saying, okay, what is the energy of my particles? And hopefully this is a negative number, right? Hopefully as they fuse together, they have less energy because they're going to release that. This is the whole idea of nuclear fusion. I can release that energy. The atom itself has less. So on the final, after they hook together, I would get 4.002602 atomic mass units minus c squared. And then, of course, the mass energy that I started with is 4.03298 atomic mass units. And so grabbing my calculator here, and I guess I still have that in my calculator, so let me put this 4.002602 minus the last answer is a negative, and okay, 0.0378 atomic mass units times c squared. And so I'm feeling good about this, and hopefully getting my point across to you that there is a decrease in the mass and therefore a release of the energy. Now I'm just debating if I should do this calculation in terms of joules, or another useful unit is called MeV per C. And so let me see what your author has. And so he has MeV, so the energies are in MeVs per nucleon. So why don't I take advantage of that? And there's a couple ways of getting there. Why don't I think it might be easier for you to understand if I switch it to joules first and then remember what an electron volt is. So this is my negative 3.030378. This is my atomic mass unit. So this is 1.66 times 10 to the negative 27 kilograms. This is the speed of light, 3 times 10 to the 8th meters per second squared. And when I do those units, you can see that's in a joule. And so then, to convert it, I'll remind myself that 1 electron volt is 1.602 times 10 to the minus 19 joules. And then working down his road, I'll say an MeV is a million EVs. So this kilogram meter per second squared cancels with a joule. This electron volts cancels off, and I will then have a number in MeVs. Okay, so this number is still in my calculator, so I'll just go times 1.66 times 10 to the negative 27. This number is 3 times 10 to the 8th, and I will square it. I will then divide it by 1.602 times 10 to the negative 19. And then the last step, I'll divide it by a million. 1, 2, 3, 1, 2, 3. Enter. And so this is a release of 28.3 MeVs. Okay, so again, I hope you see quite a bit in this picture, because like I said, I want you to see the technology for the next chapter, which is nuclear fusion. I want you to see what's meant by this chart, but I also want you to go back to E equals mc squared here, and how this is saying how the nuclear energy actually works. So this whole idea was very new to Einstein and those 30 years that shocked physics. In fact, can you really do something like this? Could you get energy from mass? Is mass just a different form of energy? And so as you look at the weights of this, you could begin to see how it works. You take 4 objects that when you put them together, they now have less mass. And the reason they have less mass is because that mass has been converted into energy, and that they gave off this energy. And in this case, putting those 4 objects together, we release 28.3 mega electron volts. Now, one last step, and because it said what is the energy per nucleon. So let me divide that by 4, and so the binding energy, which as I said is the total energy that we just calculated, divided by 4, comes out to be 7.08 MeVs. And so that's how much energy we have per each particle, and within rounding I get the same number that your author gets, the binding energy. All right, well, I hope that one was kind of helpful, and like I said, I wanted to do that one first. Let me jump back and do number 1 in the book. This will take us all the way back to the beginning of the chapter where we started this lecture, but I thought it would be a good one to do, even though we've been doing some really hard stuff compared to the start, so maybe it'll be good to see an easy one here for an example. And so I'll just put number 1 on the screen. At least I think I will. I went too far here. No, I haven't got to the problems yet. These are summary. No, these are the actual problems. So this says conceptual. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Ah, there it is. Okay. So problems and exercises. And maybe I'll make it a little bit bigger here and let it show up here on the screen. And we'll start way back with our Geiger counter. All right. So number 1 here says the energy of a 30 electron volts is required to ionize a molecule of gas inside our Geiger tube. So if you remember way back a couple hours ago, we were looking at this Geiger tube, and we said that the particles go through this. There's a little opening right there, and they go through, and as they go through, they rip those gas molecules apart. It's a kind of an organic compound that's kind of nice, because when it rips apart, it makes plus and minuses, yet they go back together kind of fairly quickly, so we can count the next set of particles here. And so this Geiger tube, it takes this much energy to rip it apart. And it says, therefore, producing an ion pair. Suppose the particle ionizing radiation disposes of a half a MeV of energy in the Geiger tube. So if you also remember, the problem with trying to count just one beta particle or one alpha particle is we just don't have the technology. These things are just really small amount of charge. We can't get one. So this is our way of amplifying it. This is our way of saying shoot through and break apart billions of little organic ones that then, because we have it hooked to a high voltage, they'll separate out, and that'll move enough charge that we can actually have our equipment sense enough to detect it. So what it's saying here is this little particle racing through, and I don't know if they say what kind it is, I'll just call it a beta particle, but if this beta particle goes ripping through and dispenses a half a MeV, it says what is the maximum number of ion pairs it could have. And so that's just kind of a quotient one. That's just simply give myself some room here to work by keeping those other equations up here, what I call the harder equations, so I can come back to them. But this one isn't anything real fancy. It's just, can you understand the Geiger tube? And so they're saying you have a lot of energy, a half a MeV, being dispensed throughout this Geiger tube, and each molecule it hits, it gives off 30 EVs. And so you're really asking, how many times does this little one fit into the big one? And that just takes me back to 4th grade, where you learned about the meaning of division, what you mean about a quotient. You're just saying, how many of these little things fit into the big thing? So we've given it all of this energy, and each one needs this much. So how many little ones can we fit into the big one? And of course, if I change that to 5 times 10 to the 5th, over 30, then we have EV over EV, which is good because then we have no units, and that's good because they ask for a number, how many. And so grabbing my calculator here, I will go 5 times 10 to the 5 divided by 30 and come up with 16,000, and I'll just do 3 significant figures. So 16,700 little organic molecules in my Geiger tube get ripped apart, and that's still a small amount of charge, but enough for this very sensitive piece of electronics to pick up, hey, something went racing through there. It tore a bunch of them apart. All right, so there's a little review of our Geiger tube. Let's go to number 9 as a third example here. Number 9 says this: go ahead and calculate the radius of nickel 58. It's one of the most tightly bound and stable nuclei. Okay, and so that kind of ties into the last thing we were just discussing, how that energy per bond peaks out at iron, somewhere around iron 55. This happens to be right next to it, or 1 over nickel, but Nickel has 2 more protons, but I think the total number of nucleons is roughly the same. They say 58. I'm just kind of curious. Nickel, 58 or 59, and very close to iron. So iron and nickel and cobalt are right up there as some of the most strongest bonds per nucleon. And so after that, you start to lose it, or before that you don't have enough. Anyways, so this one here is basically saying we have a stable, very stable nuclei. However, that's not the crutch of this problem. The crutch of this problem is just to go back to that geometry that I was saying, that each proton and each neutron each have about the same radius, which is that 1.2 times 10 to the minus 15 meters, femtometers. And then we can just raise it to however many nucleons we have times 3, or to a 1/3 power. So I'm going to put 1.2 femtometers for the radius of one individual one, and it's the 58 that is kind of the giveaway. And so that's how many nucleons we have. So taking 58 and raising it to a power of 1/3, and then multiplying that by 1.2, this looks like 4.65 femtometers. And so there's our stable one, or one of the areas of stable. So that seems to be about the strongest one. Smaller than that, not so much stable. They want to be more stable. They want to come together. Bigger than that, again, not so stable. They want to separate apart. Now, part B says, then, what is the ratio of the radius of this nickel, 58, that we just did, to, and I think we need to go look at HA. This is going to bring up an interesting discussion too, but HA 258, one of the largest nuclei ever made. Note that the radius of this larger nuclear is still much smaller than that of the atom. So this ties into what I was saying earlier. I don't care how big of a nucleus you get, it is really, really small. It is 100,000 times smaller than the atom itself. So never forget that doesn't matter what atom you look at, they all have this small, small nucleus compared to the atom itself. Now, the only thing we really need to know is that it has 258 nucleons in it. So if I were to get the radius of part B, I would do the same thing, R naught times A to the 1/3. So that would be 1.2 femtometers times 258 nucleons raised to a power of 1/3. And so I'll do that in a moment, but I also thought it might be kind of come over here to the periodic table and point out, because our periodic table does not have an HA, I don't think, in it. I'm scanning just in case I am wrong, but it should be like this area or this area. But I wanted to point out, did you notice it said ever made? Did you also notice in our periodic table that there seemed to be a change from uranium until we got to these? See, these are all human-made. Remember I said uranium was right on the edge of stability. Remember I said that it's got too many protons and neutrons, and that's why it goes under an alpha decay. It takes billions of years for it to decay. And so in the last supernova explosion, and in case you don't know, we are the leftovers of a supernova explosion. So about 5 billion years ago, you found an HA?
Yeah, there it is. It's on the, it's higher up the table, go to your left. Is that HF?
HF?
Is it hafnium?
That's hafnium. No, it's not HA though.
Oh, I'm sorry.
Yeah. I think what they're referring to is hasmium, right here.
Oh.
And on our chart, they call it HS. So what I was getting at is all these ones that are highlighted are all human-made. They don't exist very long. They probably did exist like uranium and all these other ones after the last supernova explosion, that we're the dust and we often call the belch from a supernova explosion. So that was 5 billion years ago. All these other ones have half-lives that they're all gone. That doesn't mean we can't remake them, and so what we do is we add protons and neutrons to them, and we've made all these ones, and so we give them a lot of very creative names, a lot of them related to California, since a lot of them were done at Lawrence Livermore here. We got the Californium, we got Americanism, we got the Einsteinium. Oh, here's Lawrence. Okay, so here's up in the Bay Area. In any case, what I am trying to say is, and probably should just move on to do examples, is this is an interesting discussion of that we can actually then make more that have very, very short half-lives, and that's what this one is saying. And so I'm pretty sure they're talking about this. There's not a complete agreement on what to name them and what to call them, especially since about half of these were done in Russia during the Cold War, and the other half were done in America during the Cold War, or some other Western countries. And so there's just not a cohesiveness about it. But in either case, that's kind of a fun side discussion. Let me come back to the calculation here. And so to finish up this calculation, let me put in my numbers. Yeah, Ron, you with me? Trying to look up that number a little better. Let's wait. We'll see if we can do that one. But I'm going to come over here and go 258 raised to a power of 1/3. And then this is a 6 times 1.2. And so this is going to have a radius of 7.64 times 10 to the minus 15. Well, let me just write it as femtometers. And then so your author does want you to see, you know, it's got a lot more number of nucleons, but it's really not that much bigger. And that's what I was trying to say during the lecture. And maybe to finish off the question, let's take this ratio, because I think I read how many times bigger is it. So let me take the 7.64 and divide it by the 4.65, and it is only about 64% bigger in terms of radius, okay? But in terms of its mass, or in terms of its volume, it's quite a bit, and still is much smaller than the atom. All right, well, let's move on and do some more calculations. So let's go to, what's the next one here on my list? How about number 24? Good. Number 24 has a little bit of history also about Madame Curie in here. But here it says in number 24, an alpha decay of radium-226, another isotope, the alpha decay of uranium, another isotope in the decay series of uranium. Okay, so maybe I should have emphasized, remember we started with uranium and said uranium is really not very stable. The first thing it does is send out a set of alpha particle, which is 2 protons, 2 neutrons. But once it does that, then it has too many protons, and so it goes under a beta decay. In fact, that last chart we looked at, it looks like it goes under a beta decay twice. And so a neutron turns into a proton. Neutron turns into a proton, so it has too many neutrons. I think I might have said that backwards, but it's got too many neutrons. And that's kind of normal during an alpha decay because of where that stability line is here. All right, but radium is one of those. And this was first recognized as a new element by the Madame Curie and her husband, and it poses special problems because its daughter is a radioactive noble gas. And so that means you would breathe it. And so if you're working with this and don't know what's going on, you end up breathing all this radioactive substance, and that's what happened to the Curies. I think they both died of cancer. I think Madame Curie, after getting 2 Nobel Prizes for all this work, died of leukemia. So it's kind of a sad side story. And sadly, that happened a lot with the advancement of, well, a lot of science, not just radioactivity, but a lot of science, because didn't really know what you were working with and didn't know what to be careful with. In either case, this question is an alpha decay of radium-26, another first recognized poses a special problem because its daughter is a radioactive Nobel gas. I don't see the question, and I think because up here they gave a general statement. Yeah, let's come back here. It says, in the following 8 problems, write out the complete decay equation for a given nuclei using this notation that I was talking about, of how they lose stuff. And so let me just be clear. I think they want to start with radium as the parent and see what the daughter is. All right, so let me do that. And again, let me give myself a little bit of space. Again, maybe I'll work around these equations. But this will give me a chance to do at least one example of all those little conservational principles I said, where I said if you start with some parent atom, and you go to some daughter atom and something else, that something else carries the energy, so we have conservation of energy. That something else also has to carry the appropriate charge to make sure the bottom line adds up, the number of protons, the charges. And the top line has to add up to make sure we have the number of nucleons. And so those are our 3 conservational principles. So this problem actually says it's an alpha decay. And so let me start with radium. I need to come back and look. Radium what? 226. So it's 226. And I guess I also need to come over here and find it on this chart. There it is, number 88. And so right here, number 88. And you can see now when we lose 2 protons, we're going to get over here to the noble gas radon. And so here is 88. Remember I said how this is repetitive. You can either give the symbol or the number. They're saying the same thing. And so if you release an alpha particle, that would mean you're down to 86 protons. And of course you're also down to 222 nucleons. And so again, jumping over to the periodic table, we can look at number 86, and that's the noble gas radon. And so it becomes Rn. And so this is our alpha decay. And again, a little bit of interesting history here. So this radon is a big problem, not just for Madame Curie, but for modern world we live in, because this is part of the natural decay of uranium. And so depending on where you live, and it's not too bad here in California, but pockets can get pretty bad. If you have uranium in the ground, then this decay process at this point gets radium, and the radium's a gas, and it's a noble gas. If you guys remember in your chemistry, this is the problem with noble gases, is they don't react with anything. So they're hard to even know they're there, and they don't go away, and they're a gas. And so in this case, they seep out of the ground, and normally they just kind of float away. And so if you remember my Geiger counter, I was getting about 1 beep every second. And it could have been, most of it could have been radon. It probably is, a lot of it in our area. But if you put a roof over your house and you make it airtight, it can actually come in and get trapped, and the radon can actually build up inside. And so one of the health concerns is how much radon did build up in your houses. Now, my house in particular is very old, very leaky. Nothing builds up in it. The windows leak. The insulation is terrible. So, but some of these newer homes with really good seals, or some of these places that live in cold environments or hot environments, and you really seal it up, you got to keep a little bit of a close eye on how much radon builds up in your house. Not a problem here in Santa Barbara. I seldom turn on my heater, and I don't even have an air conditioner. So it's just whatever the temperature is outside is going to be the temperature in the house. It's just the way it is. But anyways, like I said, a gas floating around. So if you're working with this stuff like Madame Curie, yes, you deserve a Nobel Prize for even finding this. This would be incredibly difficult to find. So that's why she gets the Nobel Prize in chemistry. But then to recognize its radioactivity of it and the development of radioactivity is why she got the second Nobel Prize in physics. And it's also then why they both end up breathing it all their lives, or what short lives they have, and die of cancer. Okay, well, that was what, number 24. Let me try number 45. And maybe, well, let's see how 45 goes. But I was thinking about 58 also, but I'm looking on time. Well, you know what? Maybe I'll just go along, because you guys, if you feel like you understand it, you can leave the video anytime and you'd be good here. But let me do two more, maybe of these harder ones. Number 45, I think, is one of them. And so finally I get to why I've been saving these equations, because I wanted them handy for number 45 and number 58 here, where we do some calculations with half-lives and radioactivity here. And so let's just read this 45 together. This says cobalt-60 source is labeled at 4 millicuries, but is presently, its activity is found to be 1.85 times 10 to the 7, oh, and there's that word again that I never use. Brackel? Yeah, I think it's pronounced Brackel. Is that what you think it is, Ron? Yeah? Okay, so Brackels. But I need that conversion factor. And so let me put that back on the board here, that if you have 1 Curie, that is equal to 3.70 times 10 to the 10th becquerel. All right, and so they actually gave this as a radioactive problem, but also a unit conversion. And that's kind of what I like about it here. So notice that it says when you bought the source at the local store that has radioactive something, it says, okay, the current radioactivity of this is 4 millicuries. But it is dropped down to 1.85 times 10 to the 7th. So 1.85 times 10 to the 7th Brackel. And so if I want to get them into the same unit, then I'm going to say that 1 Curie is equal to 3.7 times 10 to the 10th, yeah, BQs, Becquerel, Becquerel. I'm not saying that way. Yeah. Close enough, you say? Becquerel. Yeah. Okay, so with that in mind, let me see how many Curies I have. So 1.85 times 10 to the 7th divided by 3.7 times 10 to the 10th gives me 5 times 10 to the minus 4 Curies, which I'm going to write into 2 pieces And the reason I'm going to break down the 10 to the minus 4 into 10 to the minus 1 and 10 to the minus 3, because I'm going to take advantage of the metric system, right? 10 to the minus 3 means milli. And so this is millicuries. So I just have 5 times 10 to the minus 1, which is 0.5 millicuries. So that is the current radioactivity of this one. Now, notice that they said it started at 4. And so it's saying here, what is the present activity in millicuries? Oh, I guess that's what I just did. So I took what they said its current activity seems to be down to here. And so they gave it to me not in curies, I converted it to curies, and so that, I guess, is my answer for A. But finally I get to why I was kind of saving this one for these two problems is this decay here. This then says that how long ago did it actually have this 4 millicuries of activity? Okay, and so there is this decay, and so whether we're talking about the number of atoms or whether we're talking about the rate, as I said earlier, they both follow that same exponential decay. And there's our decay constant. And so I'm going to say my current rate is a half. So 0.5 millicuries. When the sample was new, it had 4 millicuries. And so if I know the appropriate time constant here, or decay constant, excuse me, and the amount of time, I could see why it decayed from a 4 down to a half. And so I will have e to the minus lambda t. And so when I bring 4 to this side, I have 1/2 divided by 4, that is 1/8. Now this is why I said maybe the harder mathematics I should show you, because now let's take the natural log of both sides. So I would have the natural log of 1/8, and then that would equal to negative lambda t. And like you saw me do with the half-life, why don't we think of this as the natural log of 8 to the negative 1 power? So that the negative 1 can come out in front and cancel off with the other negative. And then I can get the time if I know the decay constant. So there's another little subtlety in there. I need to know that decay constant. Well, luckily, and it's not given in this problem, and since I've been talking a lot, let me do this kind of quick. I wrote it down here. But a couple pages back, they give the half-life of cobalt there. And they gave it at 5.27 years. So let me use that over here. And this is why I was hanging on to this piece of the problem. This says lambda then is equal to the natural log of 2 over the half-life. And so again, when humans talk, we like half-lives. We don't like the decay constant. And so even though when we start doing all of our math, to solve it, we need the decay constant. So usually to finish a problem, this is what I wanted to show you, you need to come back over here and say, well, how is lambda related to the half-life? And it's this natural log of 2. And so I'm going to use that in this calculation. All right. So here's the time. Let me just do natural log of 8 for a moment. And then for lambda, I'm going to put natural log of 2 over the half-life. And then fortunately, they made my life kind of nice here, because then this would be a half-life times a natural log of 8 over a natural log of 2. And if you don't recognize it, it's fine. I would just get out my calculator and go natural log of 8 divided by natural log of 2. But 8 is 3 cubed. So you could think of this as the natural log of 2 cubed. And because of the log rule, you could think of that as 3 times the natural log of 2. And so the natural log of 2 is going to cancel off. And so this was a clever way for them to say it is 3 half-lives. That's what's happened. We have half of a half of a half. 1/8. That's what a 1/8 is, right? A half times a half times a half. So not as surprising that when we saw this 1/8 right here, we're like, oh, that's just 3 half-lives. And maybe you didn't recognize it. So I went through the math here. So we got 3 half-lives. And as I said, the half-life is 5.27 years. So this sample should be 3 times 5.27. 15.81 years old. So what all this math meant is 15 years ago, almost 16 years ago, I bought this sample. And the little package I bought it from the science store says what its activity was. And its activity was 4 millicuries. However, now, 16 years later, it's way down. It's only 1/8 of what it used to be. And that's what this is saying, 3 half-lives. Every 5 years and a little bit more, so every 5 1/4 years, it has half the activity. And it's just kind of decayed away. Now, let me use this as a springboard. I know I'm talking a lot here, but you guys in the life science probably are really interested in this when it comes to carbon dating. This is exactly what carbon-14 is. And so your author talks a little bit more about carbon-14, and rightfully so for you guys in the life science, because the carbon-14 is constantly being generated in the upper atmosphere by the cosmic rays. And so it's an assumption, but safe to assume that for the last I'll go out 60,000 years, the amount of carbon-14 in the atmosphere has been roughly the same. And since we're breathing it in and exhaling, we would just say that statistically, the percentage of carbon-14 in my body compared to the normal carbon-12 is about the same. And so when everything dies, it stops exchanging carbon. And then the carbon-14 decays away. So it's safe to assume that when something died, like a plant, falls over in the forest, it has a certain percentage of carbon-14 in it. And I think the half-life of carbon-14 is a little over 5,000 years. I want to say 5,800 and something. And so if you find this old tree and you measure how much carbon-14 is, you can go backwards like I just did and figure out how old was the tree when it died. Now, sadly, the numbers get so small after a while that this only works so far. So I think carbon-14, the best of the best, gets you about 50 to 60,000 years back. And so it's great for human activity because there are very few humans before 50,000 years ago. And so if you find an old fire pit and you want to know, okay, whatever the indigenous people were here when they were burning these pieces of wood, I can take that charcoal, I can do a carbon-14 sample on it, and I can say how old is it. And so we can then find out when those people last made a fire. All right, well, like I said, if you're still around and still listening, let's do one more here. And again, it's kind of this same little tougher mathematics with the logarithms and exponential decays. Fortunately, no calculus. We already did all the calculus here. And so let's try number, what'd I say, 58, and call it good here. All right, so 58 says, and so I'm going to come over here to 58, but it says a beta minus particle is emitted in the decay of tritium that interacts with matter to create light and glow-in-the-dark signs. Okay, so tritium, if I read this right, has a beta decay. So I'm going to start with tritium, which has 1 proton but 2 neutrons. And what it is saying here is it undergoes a beta decay. Now remember, a beta decay is no nucleons but a -1. And so that means it's going to be changing one of its neutrons into a proton and kicking out a negative. So now that we have 2 protons, we now have helium. Of course, we have what we call helium-3 because we still have only 3 nucleons. So it's not the normal helium-4, but it is fairly stable. And it's very, very useful. I don't think it's used much anymore because of our more efficient LEDs and other things, but I used to have a watch that had tritium in the dials, and so it's really nice because the radioactive decay highlights it and makes the sign light up. I think they've decided that even though the amount of radiation is a beta, which isn't that harmful, and even though it's not much, decided not to do that. So I don't think you can get wristwatches with the tritium decay anymore in them. But still, some of the signs, especially some of the exit signs, they're really nice to use. Another good example for engineering is when you're on the internet and you try to download or upload something overseas, usually there's this fiber optics that runs under the ocean. And so every couple of kilometers they put a little box because the light dims out. And so as the light comes in, it hits a little detector, and then the detector flashes more light. And to get the energy, they put in a radioactive source. That way you don't have to go down and replace the batteries to keep the fiber optics working. Satellites, the same thing. Probes, I should say. So probes we send to Mars, probes we send out and fly by Jupiter. NASA likes to energize them with some kind of radioactive decay. Tritium is a good one. Because, again, it's very light, it turns into something really harmless, it's really kind of a harmless radiation, and so that's kind of a side note in terms of the engineering. But that's why they say this exit sign. So it's an emergency exit sign, it'll glow in the dark, so if the power goes out, you'll still be able to see it. All right, so where was I? So the beta particles emit a decay of tritium. They interact with matter to create light, such as glow-in-the-light exit signs. At the time it was manufactured, such a sign contained 15 curies of H3. The first part of this says, what is the mass of the tritium? So 15 curies is quite a bit, and so how much tritium do we need for that? And so let me come over here and point out, I guess I didn't completely leave kind of the equation I'm thinking. If you remember, I started here by saying dN dt equals negative lambda times the number you have. Okay? So, if we start this problem by saying dN naught dt. So this is the initial decay. This is when you first build, I'll call it a probe to Mars. So if we're working for NASA and we're building this probe to Mars and we first inject a bunch of tritium, there's going to be this initial rate. That should be equal to minus lambda naught times the initial number of atoms that you start with. And I can solve for this. I can solve for how many atoms do I start with. And then knowing the mass of each atom, I can get the total mass of it. So what did they say? 15 And I think it was pretty big. It wasn't millicuries, wasn't it? It was curies. Yeah, 15 curies. Now, remember that a curie is 3.7 times 10 to the 10th decays per second. Or maybe I should just say number. That's how many atoms do I have. And so, oh, I didn't write that very well. I guess I should say this many decays per second is 1 curie. That's probably better written that way. So that what I can do then is cross this out and have a number here that says, okay, how many decays do I have in a given second? In fact, I'll do that number now here. And so this is 15 times 3.7. So this would be 55.5 times 10 to the 10th decays every second. So that's how many decays I have. Wow, that would be 555 billion beta particles coming out of this every second. And I know it sounds like a whole lot, but hopefully you'll be surprised at how really little this is, and so why this radioactive sample can actually last a really long time and for the life of the satellite. The satellite will die for other reasons, not because of the lack of tritium energy. And then we've got this minus, and I'll put N naught here, because now we can play this same, oops, there's not a naught here. We can play this same game here. Remember, lambda is the decay constant, but we can write it in terms of half-life. So I'm going to put half-life, and so this would be natural log of 2 over its half-life times the number. Okay. So I'm getting where I want to be, and that is how many atoms do I have to start with? And it looks like it would be 5.5 times 10 to the 10th atoms per second here. And so let me put decays per second. Let me then say if I multiply it by a half-life and divide it by a natural log of 2, this will tell me how many atoms do I have. So let me continue this calculation over here. But the other thing then I need to know, and as I said in the reading they talk about these half-lives, and to save a little time I'll just look it up. I think it was 12.3 years. So this would be 5.50 times 10 to the 10th decays or number per second. I'll put natural log of 2 down in the bottom. The half-life, as I just said, is 12.33 years. But if you'll go ahead and let me then change that to 365 days in a year, and then 24 hours in a day, and then 3,600 seconds in an hour, the hours will cancel off, the days will cancel off, the years will cancel off, the seconds will even cancel off. And again, maybe I shouldn't think of this as a unit decay. This is just a clarifier, how many decays. This is actually then a number, just how many happened. So in other words, I don't have any units, which is exactly what I want. I want to know how many atoms did I start with based on this radioactivity of it. And so grabbing my calculator, 55.5 times 10 to the 10th, multiplied then by 12.33, then divided by a natural log of 2, then multiplied by 365, then multiplied by 24, then multiplied by 3600. We're looking at 3.11 times 10 to the 20th atoms. Which again, I know it sounds like a huge, huge number here, but that's not much. Not much at all. Remember, we started this problem saying it's tritium. So its atomic number is 3. Remember, that atomic number is also its atomic mass, right? That means it has 3 atomic mass units for each atom. So now we're kind of back to 4th grade math. I've got a bunch of atoms, and I know the weight of each atom, and I want to know how many I have, or how much of the mass is going to be. And so I'm just going to kind of multiply these together. So I've got this many atoms. Each atom is worth 3 atomic mass units per atom. If you want to know, I looked it up a little more accurately and wrote it down. It's 3.02. That's not much of a change, but as long as I looked it up, I thought I would do that. Now, if you also remember, 1 atomic mass unit is 1.66 times 10 to the negative 27 kilograms. And so this will answer the question in terms of grams, how many do I have to start with? So I've got this number already in my calculator, so let me multiply it by 3.02, and then let me multiply it by 1.66 times 10 to the negative 27. And so we are looking at 1.56 times 10 to the minus 6 kilograms. That's 1.56, and I'll cancel a 10 to the 3 here, times 10 to the minus 3 grams. That's 1.56 milligrams. That's a small amount of tritium. And so sure enough, we're in the milligram range in terms of making our project go. All right, I think there was one more step to this. What else did it say here? Okay, so after some years, the phosphorus in the dials deteriorates chemically, but sorry, wrong one. There it is. What is its activity 5 years after being manufactured? All right, well, again, that's why I wanted to emphasize this equation and this equation as having the same decay. Because remember, we got it had an activity of 15 curies. And it has, remember, a half-life of 12.3 years. And so 15 years later, no, sorry, it's 5 years. So 5 years isn't even close to a half-life, right? It's a little bit under half of a half-life. And so it's not half decayed, it's half of a half decayed, roughly. So a quarter decay. So we're probably left with 3/4. But anyways, I'll wrap it up here by saying, if I want to know the current rate, I'll just take the known given rate, which is 15 curies, and call it e to the negative lambda t. And then this will give me a chance to remind you for the 3rd time that lambda is a nice number to do in terms of the math, but not very helpful to talk about it. So I'm going to come over here and say, remember, lambda is actually the log of 2 divided by the half-life. So minus log of 2 over its half-life times time. And so I've got 15 curies. Then I got E, And so I will go minus the natural log of 2. And I'll put this together. This says 5 years at a 12.33 years. And since they're both in years, I don't think there's any point in converting the units to seconds and just leave them as years. So 5 years cancels with 12.33 years. So this would be 15 times e to the negative, and maybe I'll do this in 2 steps here. So if I take 5 and divide it by 12.33, then I multiply that by the natural log of 2. We are looking at, as I said, kind of this smaller, well, maybe I better just put e to the negative of my last answer. So this is 15, and there it is, as I said, about 3/4, right? It's roughly half of a half is how much has gone away, right? Yeah, maybe I better collect now because it's not quite half of a half. Anyways, I'll finish this then by saying it's 15 times my last answer, and we're still looking 5 years later at a rate of 11.3 curies. All right, well, I hope those math ones really helped because, like I said, they've got those natural logs in them. And so if there's anything that's going to probably be a challenge, I think, on the homework, it's really this math. And so I wanted to spend some time on those. All right, I'll call it quits for now and see you next time.